ISEE was founded in July 2022 to address these wide-ranging issues from ecological and social impacts of climate change, renewable energy plans, governmental policies to address regulations, and educational outreach for students and communities. And that educational component, which is certainly part of the symposium today, is a central platform of the ISEE vision. The Institute bridges the interdisciplinary needs to address climate change in a partnership between the College of Humanities and Sciences, the College of Engineering, and the L. Douglas Wilder School of Government and Public Affairs. That interdisciplinary nature very much, of course, brings to mind the language that we think about from someone like Rachel Carson, who talks about the fact that in nature, nothing exists alone. So too, in our solution for energy and the climate crisis that we are living with, we have to think interdisciplinarily, collaboratively, and certainly not alone. We have a full schedule this morning for this early plenary address, so I'm going to be brief in my introductions. I would just like to say that I know this inaugural symposium is the first of what I hope and am quite confident will be a series of public symposia, bringing people together to talk about these pressing issues in important and in meaningful ways. We're going to kick off this morning with some welcoming remarks from the president of Virginia Commonwealth University, Dr. Michael Rao. He needs no introduction, but I will say that he is someone who is a champion not only of collaborative relationships like this, but the kind of interdisciplinary synergies that make this institute and this conference possible.
I want to say thank you to Catherine. I really appreciate the support that you've lent to this on a more daily basis than I. And I certainly appreciate the support that the research office and my colleague and my vice president, Sriram Rao, has given to this effort. But most of all, and of course, I want to thank all of you for being here. I very much appreciate that you're taking the time to work together with us in this really critical intersection of energy and the environment. But the most important thanks I need to give is to our visionary and to the person who has really been an international expert in this space, and that is Puru Jena. Puru has been a part of VCU for many, many years, but he's also been an incredible source of energy himself in terms of bringing people together, bringing some of the best ideas together. And really, this whole intersection of this multiple disciplines is a critical part of what we're really trying to achieve with this. It's going to take a significant amount of time. It's going to take a significant level of engagement with people of all ages, at all levels, and from so many different disciplines that we have not necessarily thought about. We typically have done so much of what we've done in our scientific silos and in our social science silos and so on and so forth. And that is where we've gotten made a lot of headway. But I think going forward into the future, if we want what I will call a real transformation, we're going to really have to bring together all of these folks that I'm talking about. Just yesterday, Puru and Catherine and I were together when we, I would like to say, broke the champagne bottle. We actually cut the ribbon on the new STEM building, the VCU STEM building. It's a really cool building. I have to say it exceeded so many of my expectations. But one of my expectations is that it will be a high-level LEED Platinum certified building. I don't know if we will achieve that. We won't know until the building is completely done, but I am really excited about the possibility that that might happen, and it certainly was my goal. What we've got to figure out how to do is to address something that actually came up right here in this room when I was together with the NSF director, the National Science Foundation director, Panchanathan. And this was maybe a month and a half ago, something like that, together with Senator Tim Kaine and Congressman Rob Whitman. So we were sitting here in this room together, and Panch is who our director, that's the name that he goes by. Panch basically said, you know, this is one of those institutions that really matters. And so I said, well, tell us more about that. He said, because you will be one of the few institutions in this country, if not the world, that has the greatest opportunity to help us capture the missing millions, the millions of people who have the tremendous potential to be a part, an important part of science and really creativity and understanding what we all need to understand. And we are missing millions. And that's one of the great things that when I was talking with Puru this morning, I was so grateful to hear about. And that is his target at K-12, engaging students and people at all levels. And we are missing millions and millions of people. Science cannot just be for a select few. We are in deep, deep trouble if that's the case. And that's not the case in the goals of this undertaking. And so we've got to have more innovation. We've got to have more different ways of thinking critically about how all of this works. And we've got to have more disciplines involved in thinking through how we deal with the realities of how we live as human beings, the needs that we have for energy, and how to sustain an environment that we know we need to deal with. We know it, right? We see signs of it all the time. The things that we have done as human beings, mostly, hopefully, well, including us, but human beings who have come before us, we just know it can't go on forever. And so how do we find ways through what we have been given, which is a tremendous amount of intellectual capacity? How do we figure out how to take these next phases of human life, the human experience, to a level that could be even better? So we have a lot of opportunity here. That's why Puru has done a great job of bringing so many great people together, not only so many of our colleagues from VCU, but also Costa's here from OSTP. Josh is here from the Secretary of Energy, which Puru has worked with for many, many years. One of our pioneers in the DOE space. Senator Hashmi will be here from the state, along with others from the state. Our national labs have experts who are here with us. And then some of our commercial partners as well, like Dominion Energy. And then of course we'll have many people from our own focus, our own places as well, the Wilder School and others that Catherine mentioned. I would say, as we think about one of Puru's really important goals, which is to engage so many of these millions who have not been on this pathway historically, we've got to find ways to think about how differently our students who are coming are going to expect their experiences to be than the ways that we have done them. So I would ask us to give thought to a lot of things in the scientific context, in the policy context, but also in the educational context. And one of those is that the Oxford and Cambridge ways of learning work for people who are at Oxford and Cambridge. I'm just telling you, I don't necessarily have a full opinion about this myself. I'm just being observant about the realities that the ways that we tend to communicate with each other and try to teach each other are not all of the ways in which most people seem to want to learn. So I'm not saying that we have to fight that. I am saying that we have to deal with it. And so as we deal with it, one of the things that I'm finding is that when we can give students in particular a context in which what we're asking them to learn starts to make sense to them and gives them a reason and motivation to want to learn that, it helps them enormously. It helps them enormously. This generation of young people want to make a huge difference in the world that they are a part of. They're more concerned than most generations have been about the people who will follow them. And we need to think about that. I really think there's an opportunity there. The other thing that I really hope for this institute as we kick it off is that we can do more to truly be as resistant to undue influences as possible and just focus on what we know has to be real. There are so many different influences. We have lots of reasons to now be more aware of those influences. We've got to be cautious about them. We got to be careful about how we navigate them, right? Because we want this to be a sustainable institute of sustainability. So with all of that, I'm very grateful to all of you for being here. Very excited about what this will do. And of course, I am absolutely issuing license to do what's right, and to stay away from the undue influences. from those areas where we really don't have a lot of evidence and where it's going to be dangerous for us to go, because winds will go this way and then they will go that way. And we need to stay where we know we can stay and make a positive difference that will be more geared toward what we know is the truth. So with that, thank you. Puru, I don't know how to thank you enough. You have so much on your plate. You have done so much. You have so many options. You could be anywhere in the world, and you often are everywhere in the world because you are in demand. But I do want to say to you, thank you for your leadership of this institute. It's something that we really needed, and you're the right person at the right time. I'm excited about what you're going to do, and I'm really grateful for the influence that you have leveraged to bring so many great people together. You know so many people in this world, and you brought them together to help us launch this in such a great way. Thank you.
Thank you, President Rao, who hit, of course, the key significance of ISEE and what it's going to mean. Now, Puru cautioned me to be brief in my introduction of him, which I will be because I know I'm on the clock. I'm watching the minutes tick by, but it wouldn't be appropriate for me to not recognize certainly the energy that he has brought to this initiative and his role as literally a distinguished professor in the Department of Physics in the College of Humanities and Sciences, and of course, as the director of this new institute. I would be here all morning if I list every recognition, both nationally in the Commonwealth and across the globe, that he has received. So I will withhold my remarks in that, but I will say that he is an amazing collaborator who has brought together so many important people across campus and across the globe, not just this moment, but to lead forward this really important initiative. So I know that I have a real sense of gratitude toward him, as I know everyone in this room does. But without further ado, I want to give him the opportunity to provide the introductory remarks to this wonderful symposium.
Dean Garcia. I'm sorry, President Rao has to leave for another meeting. My distinguished colleagues, ladies and gentlemen, good morning. I'm not very good at public speaking. So I wrote down what I want to say, and I hope I will be able to go through it. But in any case, on behalf of the organizing committee and the membership of what we call ISEE, Institute for Sustainable Energy and Environment, ISEE, I welcome you all to the inaugural symposium. This is more than 6 months in the making and the result of a 15-year dream. I'm delighted that VCU instituted science, energy, and environment as one of the 4 strategic areas for focus at VCU. And I would like to thank Dr. Sriram Rao, who is actually trading place with you in DC, for making this institute a reality. If you just look around, melting ice in the Arctic, rising ocean temperature, and the effects it has on marine life, the devastating floods in Pakistan that killed thousands of people, droughts from California to Africa, wildfires from our country's west coast to Australia, and the record number of tornadoes in the USA in the month of January. We have already passed the number of tornadoes that we have in a year by now. All are signatures of a changing climate. And this change is the result of global warming caused by fossil fuels that undoubtedly changed our lives and our economy, but it came at a cost. Sadly, the countries and the people who contributed the least to this catastrophic change are suffering the most from it. It is our moral obligation and responsibility that we do everything in our power to mitigate these adverse effects, not for ourselves, but for our children and their children. And this is not going to be easy because the issues and challenges in energy and environment are complex and intertwined. It affects all aspects of our lives and it touches everyone. No one wants to change his or her way of life, and we do not have the moral standing to ask developing countries to slow their economy by consuming less energy. We must therefore transition from fossil fuels to a clean energy economy while still maintaining our way of life. Until that happens, we must find ways to capture, convert, and sequester greenhouse gases, find cost-effective and innovative ways to increase our use of clean, renewable energy, ensure a sustainable future, secure our energy grids and increase energy efficiency, find environmental justice, develop sound policies driven by science and not politics, educate our students and the public, and work with our global partners to expedite these initiatives. We need our scientists to develop fundamental understanding of material properties that will lead to the design and synthesis of novel materials made of earth-abundant materials and capable of meeting the requirements of the next generation devices. Of energy production, storage, distribution, engineers to take innovations from the laboratory to the marketplace, economists and industries to work together to make these devices safe, durable, and cost-effective, policymakers to make these transitions seamless, and the public to understand that we are all in this together. And maybe our judicial system should be proactive in protecting the environment, and it will take a village. This is exactly the goal of ISEE. It is composed of faculty from the entire university and across disciplines with a diverse expertise. They include physicists, chemists, biologists, mathematicians, electrical, mechanical, and biochemical engineers, medical doctors, social and political scientists, humanists, artists, and policy experts. You will see some of their works featured in this symposium. Our eventual goal is to make this institute a global center where scholars from across the nation and the world will come together to address outstanding challenges and find innovative ways to solve them. We are fortunate that our invited speakers are world leaders in their own disciplines, and they are comprised of scientists, engineers, social scientists, policy experts, environmentalists, ecologists, lawyers, and lawmakers. They come from local and federal government, national laboratories, academia, industry, and the public sector. I'm sorry that Stanley Whittingham was awarded the 2019 Nobel Prize for his work on lithium-ion batteries, and Emma Kemp, an expert in the effect of climate change on coral reefs and National Geographic Explorer and Times Magazine's Next Generation Leader from Sydney, Australia, could not be here in person. But we will view their presentation through pre-recorded videos. We look forward to learning from all of you and help for collaboration. Putting this symposium together has not been easy, as speakers from many disciplines have come. I'm grateful to the organizing committee members, Supriya Bandyopadhyay, Radhika Barua, Natasha Lewinsky, Andrea Simonelli, and Weining Wang, the two associate directors of ISEE, Otul Jayasimha and Damian Pitt, faculty members of ISEE, and our student and postdoctoral volunteers, staff members in our Dean's College, and not the list, at the list is Rani Sisabat, Administrative Assistant of ISEE, for their advice, guidance, and great effort. I'm also grateful to Catherine Ingracia, Dean of our college, Dean Gary Tepper, Dean Susan Gordon from the Wilder School, for all their support and generous help over the past year, and I hope this will continue. I'm very grateful to President Rao and Sriram Rao and our provost, Dr. Fotis Sotiropoulos, for their help to support this symposium. The symposium is also funded by the Department of Energy, and I'm thankful to all the invited speakers for taking their time to come to Richmond and be part of this inaugural symposium. And last but not the least, I thank you all for coming. I look forward to 2 exciting days of learning. Thank you very much.
Thank you so much, Guru. We certainly are all in this together. So your words are really resonant. Joining us from afar is, we are delighted to welcome Nobel laureate and professor of chemistry and director of the Institute for Materials Research and the Material Science and Engineering program at SUNY Binghamton, Dr. Stanley Whittingham. Dr. Whittingham is known as the founding, as I'm sure everyone in this room knows, but I feel obliged in case someone needs to be reminded. Dr. Whittingham is known as the founding father of the lithium-ion battery, used ubiquitously in cell phones and now electric vehicles. After earning his doctorate from Oxford in 1968, Dr. Whittington developed an innovative cathode in lithium batteries. He holds the original patents on the concept of the use of the intercalculate chemistry in high power density, highly reversible lithium-ion batteries. He also invented the first rechargeable lithium battery metal battery, patented in 1977 and assigned to Exxon for commercialization in small devices and electric vehicles. In 2019, Dr. Whittingham, along with John B. Goodenough and Akira Yoshina, were awarded the 2019 Nobel Prize in Chemistry for the development of the lithium-ion batteries. Storing electrical energy in batteries is a key factor in solving the world's energy supply, and we are delighted in welcoming Dr. Whittingham virtually.
Hello, everybody. I'd like to make a few introductory remarks for your symposium, and I'm going to talk about how important energy storage is in the electric economy for a sustainable future. If we look at all the issues we've had with climate change and the global messing up in the last few years, I show you 6 examples here, spread around the world. Flooding, tornadoes, excess warming in, say, Canada, fires. It doesn't matter where you are, we got more extreme examples of this. We together have undergone 2 disruptions in our lives in the last 30 years. We've undergone the communications revolution, which has been enabled by the lithium battery. 30 years ago, you would not know instantly what is happening the rest of the world. With the communications we have today, you know exactly what's happening throughout the world. And this has really changed the lives. And any of you who teach, see the students are very active looking at what's going on somewhere else. More recently, we've had COVID. And COVID has shown the challenges of a global supply chain, which is clearly not tenable anymore. But it's also shown how we as humans can react and come up with fast vaccines. Now we have to adapt to climate change. We can control it. I'm not sure we can roll it back. But to do that, sustainable materials and processes are key. We need to get rid of all fossil fuels and use clean, lower cost, renewable electrical energy. Solar and wind plus hydro are going to dominate in this renewable area, but they are intermittent, at least the solar and wind. So we have to store energy. And lithium batteries are the key ways of doing that. Let's just look at how this field has changed in the last 50 years. I show you here two examples of the first lithium batteries ever made, a paperweight, and then some larger batteries used for electric vehicles. And this was 50 years ago. Where do we stand today? Every sort of vehicle you can think of, you can buy as an electric vehicle. A cleaner vehicle, less polluting, less health issues with them. And at the bottom, I show you 4 examples that London Transport are trying out to see which is best for their circumstances. Whether it's a hydrogen fuel cell bus, an all-electric bus, a hybrid bus, or a diesel bus. We have many options. Similarly for grid storage. Today, solar and wind are lower cost than new coal or new gas power plants. So economics are driving adoption, not necessarily politics. And I show you 3 examples here. One in West Virginia, a wind farm, one here in Binghamton. And these are more than 10 years old, so grid storage has been around. And in the center, the world's largest grid storage facility in Moss Landing, California, which is used to store the excess solar energy in the middle of the day. So what do we need to do for greener, safer energies? We will clearly, in my mind, use lithium battery systems for the next 5 to 10 years, plus pumped hydro. I should emphasize pumped hydro is an extremely sustainable system, also the lowest cost system, but there's not many opportunities to improve that. But if we're going to use batteries, we've got to have new manufacturing technologies. These have to be sustainable. We have to leapfrog the Asians in the manufacturing methods. And we have to go back and use clean mining with clean energy. For example, use electroreduction to replace carbothermal. We have to recycle, reuse everything we make. So in the case of batteries, we need to recycle those batteries. And when we recycle them, we have to keep those materials in America for our own use and not send them overseas. This will give us a sustainable society with clean chemistry. The other key thing we have to do, we need new manufacturing in America done by Americans. And this is essential if we're going to have a sustainable society. Today, some battery materials travel 50,000 miles from the mine to the finished product. That is untenable. It has to be reduced. So please have a great meeting. Enjoy yourselves.
Great. Thank you very much. Now we are honored to welcome our keynote speaker for the symposium, Dr. Costa Samaras. Dr. Samaras serves in the White House Office of Science and Technology Policy as Principal Assistant Director for Energy and OSTP Chief Advisor for Energy Policy. He works with the OSTP Director, the Deputy Director for Energy, and senior leaders throughout the government in coordinating federal activities and direction on U.S. energy technology policy to meet President Biden's goal of a net zero emissions economy no later than 2050. He co-leads a whole of government effort on innovation in energy systems data and assessment to support a clean, rapid, and equitable energy transition. He also leads the Biden-Harris administration's assessment of the climate and energy implications of crypto assets. His talk today, Launching a Transformative Decade of Climate Change, of climate action, which also I think will see climate change, promises to discuss the future of our nation and our planet in the next steps to address climate change. Please join me in welcoming him this morning.
Thank you so much, Dean Ingracia, President Rao, Professor Paroof Jaina, and Ronnie Sisava for this lovely invitation to this most joyous occasion of the opening of ISEE. I'm very grateful to be here. It's an exciting time in energy. I'm going to talk a little bit about what we're doing in the federal government and looking forward to our continued partnership with universities and innovators around the country. I'm going to talk today about launching a decade of transformative climate action. I want to acknowledge my deputy director who runs our energy team at the White House Office of Science and Technology Policy, Dr. Sally Benson, and our energy policy assistant, Rachel Rioffi, who has worked on these topics with us. So I'm from OSTP, the White House Office of Science and Technology Policy, and we serve as the science advisors on all things technology and science to the president and to the executive office of the president in the White House. And in that office, Dr. Benson leads our energy team. And what our energy team does is bring science and technology expertise to our energy transition from OSTP. And so we lead assessment of how we can get all the way to net zero and what types of innovations are necessary in our energy system to get there. And we also understand the interactions between our energy system and our other systems, as well as our energy system and not just engineering and science, but social science as well. And I am thrilled that Dean Ingracia is here, and I'm thrilled that this center intersects between engineering, humanities, social science, business, because that's how we're going to get this transition done. And I'll talk more about that in a minute. So I'll go through this quickly so that we can get to the coffee break. That's probably what we're waiting for. As Professor Jaina has talked about, climate change is not an environmental problem. It's an everything problem. And it requires a solution across all disciplines. And the important thing to understand about climate change is every ton matters. Every 1/10 of a degree matters. Every year matters. And that climate change is not going to, we're not going to approach the 1.5 or 2 degree thresholds and declare victory or declare failure. Every bit of success that we have now improves the lives of everybody that we know now and everybody that comes in the future. The IPCC, as well as the US government National Climate Assessment, and all scientists and engineers around the world who have looked at this issue say, we need to get to net zero. And we need to get to net zero rapidly to avoid the most dangerous impacts of climate change. But a clean energy transition affects everything. It affects, of course, the environment, but it also affects equity and how the people who have contributed the least to climate change, as Professor Jaina has mentioned, often bear the brunt of some of the most extreme impacts. It affects the economy and the ways and the opportunities that we want to grow a new economy from the bottom up and the middle out. It affects security and our national defense and our supply chains. And it affects the way that we interact as a society on the future. Climate change sets the landscape on which the future unfolds. So we need to get to net zero and quick. But that is necessary, but not sufficient. We have an opportunity in this transition to do this with everyone and leave nobody behind. And that is very, very important to the president. So in this clean energy transition, we are going to get to net zero. We're going to create good paying jobs. We're going to increase equity and advance environmental justice. We're going to increase our national competitiveness, and we're going to enhance and increase energy security and reliability. So what have we done? On his first day in office, the president rejoined the Paris Agreement, and since has undertaken a historic set of actions that have advanced climate change action in the United States. So we have an agreement under the Paris Agreement to reduce our greenhouse gases emissions by 50 to 52% by the end of the decade. The president has committed 100% carbon emissions-free electricity by 2035 and net zero emissions no later than 2050. But one thing that may have gone under the radar if we're not working this day in, day out, is the president's executive order on federal sustainability in December of 2021. And what that does is lead by example and really set the opportunities that an administration has to demonstrate and deploy advanced technologies inside our federal agencies. So federal agencies are going to use 100% clean energy by 2030. Federal agencies are going to purchase 100% clean vehicles by 2027, or that. So I'm a vehicle person and kind of a electric transportation person. That by itself, I think, will catalyze an entirely new era of innovation in our electric transportation because it's not that far away. We're going to have net zero buildings, and we're going to build capacity and know-how that starts in the federal procurement and bubbles out into the private sector. President committed to environmental justice from day one and launched a Justice 40 initiative where 40% of the benefits, many of these programs, are going to go to programs that have historically been left behind. We're also building a new energy economy with manufacturing jobs, advanced manufacturing jobs right here in the United States. Our solar manufacturing is 3 times today what it was before. We have unprecedented amount of investment in lithium-ion manufacturing in the United States. And we have a comprehensive assessment of our supply chain to figure out how we can do this clean energy economy better and grow opportunities for all. You may have heard of the bipartisan infrastructure law, and if you haven't, I'm going to tell you about it because it's very exciting to all of us, and I hope all of you. Bipartisan infrastructure law has more than $21 billion for clean energy demonstrations in hydrogen, in carbon capture, carbon dioxide removal, and advanced nuclear. It also accelerates leasing for clean fuels and clean energy on federal lands. Just a tremendous infusion of the federal energy R&D space happened under the Bipartisan Infrastructure Law. And then there is the Inflation Reduction Act, which is the single biggest investment and opportunity in climate action by the United States, in history. More than $370 billion are available to catalyze a clean energy economy for everyone here in the country. So there are incentives for clean energy generation. There's incentives for clean fuels, clean hydrogen. There's incentives for energy efficiency and home improvements. There are electric vehicle incentives that are coming out that are growing a new electric vehicle economy here in the country. And there's all types of other ways that this is going to enhance and grow good paying jobs here in the country, including bonuses for communities in our legacy energy communities. And so this is an agenda that is designed to grow a clean energy economy for everyone. It also is an agenda, if we take it from the perspective of a center like ISEE, to find ways to contribute and advance energy innovation so what starts here grows from around the world. So there was a long-term pathway that the United States put out in the fall of 2021 that says, here are some broad opportunities to get us all the way to net zero. I'll note that carbon capture and carbon dioxide removal provides 10 to 20% of the emissions reductions in the pathways that the administration had mapped out in the fall of 2021. But there are opportunities here for all the things that energy centers like ISEE and the research community and the startup community are excited and working on in buildings and transportation and in industry. So like any long-range plan, the university administrators like to make long-range plans. There's lots of bullet points, but let me just focus on 2. Net zero electricity by 2035 and electrify light-duty transportation, heating, and a big portion of industry. Those 2 by itself are going to require innovations and action from folks in this room and from around the country. So for these pathways, there's no right answer. The only right answer is on the right side of the equation, and that is equals zero, right? Everything else on the left side is up to the innovators in this room and around the country. And so as long as we get to that, those opportunities that are consistent with the values and growing the good paying jobs in the United States, there are different pathways that we can take to get there. We know the broad contours. But in the electricity sector, we know we need to deploy lots of renewables. We know we need lots of energy storage. We know we need clean, firm power. And we know we need to understand how these are going to interact with each other as we're growing the electric sector. And I'll talk more about that in a bit. So today, as this is familiar to many in this room, but when we go out and talk about this, we want to hammer home the importance of systems thinking and systems analysis in the energy transition. Today's energy resources are providing energy services. We want cold drinks, we want hot showers. Those are converted depending on how we're generating those and delivered. And we're ultimately getting these services in our homes and businesses in our industry. But all of these components, resources, conversion, transport, and use are interacting in near real time and all have to work all the time. And real-time delivery is built across a century-old legacy of how the system works. Now we're layering on top of this new and digital technology. So the interaction of the cyber-physical is critical on the way that we transition this new energy economy. Because we need a deeper understanding of energy systems integration. We need a deeper understanding of how we do optimization and coordination for when we have new resources that are variable. We have new resources that have different supply chains. We have new resources that are going to different parts of the country. And we have new demand as we grow the economy and as people are both here and around the world use more energy. So real-time delivery is going to get more complex. That doesn't mean that it's, and so again, if it gets more complex, as long as we can still deliver cold drinks and hot showers, that's what that's what society deserves. So it's up to the innovators in this room to figure out how to manage this complexity. Electricity is likely to become our primary source of energy for more than half of our end uses. As we electrify our vehicles and our heating and much of our industry, and as we think about generating new ways to do hydrogen production, our electricity system is the backbone on which the future clean energy transition unfolds. We're going to need end-use devices that respond in real time to supply side signals and interact with the grid. We're going to need two-way power flows and distributed sensors. And we're going to need the computational tools to model and understand how this all works. Now, as you all know, a model is only as good as what you put into it. And so as you're building these models, I'm encouraging you to work with the social scientists, work with the business community, and work with the rest of the community that is centered here in ISEE to understand, well, the model said on paper that everybody wants this. Well, is that true? Did it happen? Why didn't it happen, right? And building that expertise into our assessments, into the models from the beginning can ensure we have more success at the end. But of course, there's lots of engineering and science opportunities, new science, new equations, new ways of doing things in control and optimization, in collecting data and doing real-time analytics. I think it's important that we've been able to make a giant leap between, say, 2000 and today in the way that we manage and understand our energy system. But we still have a lot more real-time assessment and real-time intelligence to go to deal with this giant moving project of decarbonization. And so there's three critical and interconnected challenges around this first part of this that I'm talking about. It's advancing electrification while leaving nobody behind, while also decarbonizing the power grid, while also dealing with what we heard about from Professor Jaina, that our energy system has historically been a driver of climate change, but our energy system and our infrastructure are also on the receiving end of the impacts of climate change. So as we design a new energy economy, it needs to be designed for the climate and weather of the future, not the climate and the weather of the past. And as we make sure that people are safe from extreme weather and safe from climate damages while we're redesigning this infrastructure, it can't look like it did before. So I have been mentioning electrification. I just wanted to show a couple different pieces of why that's important. And so what this is showing is that the type of energy that is used in many of our devices varies. And as we might expect, nearly 90% of our energy in our transportation system is from petroleum products. And so when we shift from a petroleum-dominated transportation system to an electric vehicle, because petroleum plays a very, very small part in our electricity sector, less than 1% in the continental United States, we're basically shifting completely away from petroleum products into the diverse fuels of the electricity sector when we electrify our vehicles. So there's a large opportunity to increase energy reliability, energy systems, decarbonization, and reduce pollution by getting to electric vehicles. Similarly with space heating, about half of the space heating in the country is from natural gas. And as that can be electrified with very efficient heat pumps, which by the way, there are tax credits and incentives under the Inflation Reduction Act, that's another very near-term opportunity to shift from a carbon emitting source to one that's potentially less carbon emitting. And again, as we move down into industrial processes and other buildings and agriculture, electrification provides a foothold for the energy transition. And we should be finding ways to make it work, make it affordable, make it accessible, and make it rapid. So we are going to have to accelerate electrification at 4 times the historic pace. And if for those of you who have been in the utility sector or been thinking about or been working in the electricity sector, the electricity sector has basically been on a kind of flat load growth over the last decade or so. And we're going to have to return to the growth mindset, growth and abundance mindset of how do we ensure that we have electricity and electrification for everyone while make sure that it's reliable, affordable, and clean. And that's going to require how we design new devices, both in the generating side, transmission, distribution, and at the end use. It's going to require all that optimization that I talked about and making sure it all works together. But then the last part that I promise I didn't put here just because it was the center here at ISEE. ISEE has a social science and humanities component. This is very much at the heart of what we do at OSTP, is bring together the social sciences, the finance, and the engineering and sciences, because that's how it's going to work. So this last part on the bottom is social and institutional innovation and how these types of technologies, new technologies that folks may not be familiar with, new technologies that folks may find risk in. How do we make sure that the risk is reduced, that the benefits of new technologies are harnessed for everyone, that the impacts of new technologies are minimized and do not disproportionately fall on communities that have historically shouldered a lot of risk? This is foundational to the energy transition. So one example here is, why electrification can help immediately, is that a lot of the urban air pollution in cities comes from the transportation, tailpipe exhaust from the transportation sector. And as we can move that tailpipe exhaust to the electricity sector, where we have increasingly cleaner generation, we can immediately remove a lot of the ground air pollution in communities that are overburdened and dramatically improve health outcomes. So this is more than whether an electric car is fun to drive. It is. And whether an electric car is cheaper to drive. It is, by about 70% in most cases. This is about our neighbors and ourselves breathing cleaner air. Now, you thought that by itself is a reason to advance in the energy transition. Here's where communities like this need to step up and step in. If we think about the types of loads that you have in your home, Maybe you have an electric water heater. Maybe you have an air conditioner. Maybe an electric clothes dryer, dishwasher, right? I've put here the approximate, and I know Professor Jaina is probably going to tell me and I've gotten some of the numbers wrong, but I'm close, right? So imagine there's error bars here. I put here the approximate loads of those devices that we count on, rely on all the time when they're running. And so if I add 2 electric cars to a household load, I can nearly double the peak load. And we need to make sure that every part of the energy system is ready for that. In most places it is, but we have to make sure that as more and more adoption of these electric technologies that are benefiting consumers and the environment happens, that these technologies are integrated smartly and the energy system reliability is increased. As neighborhoods electrify with new devices and new vehicles, we will need to pay attention to our local distribution system. This is the first line of defense and infrastructure that we should be paying attention to in electrification. I worked in electrification for a long time, and a very good question that people ask is, do we have enough electricity to power all these new vehicles? The answer is absolutely. And a kind of a good rule of thumb that I always use, if you flip the entire US light duty vehicle fleet over to electric tomorrow, you'd need about another 25% total kilowatt hours that we generate. So we're not going to flip it over tomorrow, but we're going to do it very rapidly. But that gives you a sense of scale of what that would mean for the grid. Now, we need to advance our light duty electrification rapidly and advance our other appliances electrification rapidly. And so what that means is the power plants are important, but the first piece is the kind of invisible infrastructure around us, distribution lines, distribution transformers, substations, transmission. So as neighborhoods increase, these are opportunities for our engineers and scientists to think about optimizing and deploying new technology. As our regions electrify, now we need to make sure that we have regional transmission capabilities. We need to make sure that we have more smart generation so that we can meet the needs of a growing electric economy over the coming decades. So what are the actions to get to our Paris Agreement targets? Well, we're going to deploy, as Jigar Shah of the Loan Program Office says all the time, and we're doing that. Solar, wind, batteries, efficiency, transmission, and charging stations. The president has made a commitment to install 500,000 charging stations by 2030, and we're well on our way to making that happen. As I mentioned, the bipartisan infrastructure law provides large-scale demonstration project resources to really prove and grow the types of learning that happens when you build something, when you put steel in the ground and you make that happen. And also, we're not taking our eye off the ball. We can do all these things while also invest in game-changing innovation. And so this is not, there's an old kind of battle between deployment versus innovation. We will need both and a lot of both. So we need new systems thinking with urgency around innovation and discovery-based research and applied research. So along with deployment, we have to ramp up our innovation cycle. And that's the last part of the talk. I'm going to talk about that. Our long-range plan that I mentioned before creates a blueprint for the bounds of the transition. And now it's up to the innovators and the researchers and the firms to figure out how do we get from where we are down to zero. So our office, the energy team in the White House Office of Science and Technology Policy, led an interagency effort on U.S. innovation to meet 2050 climate goals. We released this report last year, and we worked with 17 agencies across the government, including very much our good friends and partners at the Department of Energy. And what we did was look at what are the technology areas that will be absolutely essential to increase the likelihood we get to zero faster, cheaper, and more equitably. And there's a lot, right? We identified 37 to start with. And so these are across all the sectors of the economy, in transportation, in electricity and industrial, in buildings, in agriculture, and in carbon removal, as well as a whole bunch of things that cut across these sectors. And so this report is published on the web. I'm happy to talk more about it, but I encourage you to go through that because that is the type of opportunities that are wide open. Imagine being, for the students that are in the room, you are at the beginning of this new era of science, engineering, and research in social science, that the table is wide open to do really amazing things. In order to identify these and start to advance some of these game-changing opportunities, we didn't just look at cost. We didn't just look at technology availability or technology feasibility. Now, don't worry, mechanical engineers, we still obeyed the laws of thermo, right? So that we made sure that it's technically feasible. But beyond that, we have to go to understanding, can it get us to zero? Is it necessary to get us to zero? What are the impacts for jobs and for disadvantaged communities and for environmental justice and for global energy access? What are the opportunities for broader impacts across the economy? What are opportunities to increase security and reliability? So this is what we call a multi-objective framework, right? As the researchers will attest to, sometimes you optimize for one variable, sometimes you optimize for many variables. All these variables need to be at 100, right? So there's no discounting of any of these important topics. They all have to be maximized. So I won't go into this, but this is evidence of a multi-objective framework across different attributes and across different technologies. And this is the process that this group went through to think through, how do we get to net zero across these 37 game-changing technologies? And so we identified which ones would have transformational impact, right? This is impact across lots of sectors. We identified the ones that have broad impact, and then targeted. And so we worked on targeted. We wanted to say something that didn't mean small, right? Because targeted does not mean small. It just means it focuses on one sector of the economy rather than every sector of the economy. We are going to need, near zero CO2 aluminum and steel and cement. And we're going to need electric and hybrid aircraft. And we're going to need no CO2 shipping. Again, these are innovation opportunities for entrepreneurship, and discovery that are wide open. So I'm going to talk about, in this last bit of the talk, the first 5 of these. So you start with 37, and we said maybe we just, after we identified the 37, our next step was let's start with 5 and work with our agency teams to say, what do we need to do for these 5? And then we'll repeat the process. And so now we're diving into a couple of these to start with. So the first one, as you might expect, net zero power grid and electrification. So this is really about the end uses. And this is about making sure that we can enable a distribution system that manages all of these new loads that I've been talking about and increases energy system reliability and resilience. This is a kind of a multi-tiered effort to connect generation, transmission, distribution, and end uses all in one place, so that we're doing this research across these different spaces. Because sometimes you push on one thing and something else pops out in another direction. We need to have all of these connected from the beginning so that we're advancing electrification for everyone. So the next one, and I don't want, maybe the folks in this room don't get bored with air conditioning. I love heating, ventilation, and air conditioning. Very important, right? It's both super interesting from an engineering perspective, but it's also very important from a public health perspective. Because as climate impacts advance, ensuring people have adequate cooling is a justice issue. Ensuring people have access to heating in the depths of winter is a justice issue. And so we need to make sure that heating, ventilation, and air conditioning is affordable, accessible, widely distributed, and uses refrigerants with very, very low global warming potential. And so there's all kinds of innovations that can happen on designing new refrigerants, designing new systems, deploying new systems, the social innovation of how systems are advanced. As I mentioned, there's Inflation Reduction Act tax credits. But this is, how do we ensure that as we're electrifying our heating system and adding air conditioning, that we're doing it in a way that advances all of these objectives? So the next one, this one's challenging, right? Net zero aviation is an innovation opportunity. Let's look at it from the positive. What engineering challenges does the innovation community have before it for net zero aviation? Lots. We want to enable people to have mobility, and it needs to be with zero carbon or net zero carbon. And so there's going to be new innovations in bio-based net zero jet fuels. There'll be new innovations in electrochemical net zero jet fuels. There'll be new innovations in electric and in hydrogen. And there'll be new aircraft designs and new opportunities for mechanical and aerospace engineering. There's also new opportunities for assessment of impacts of all these innovations as air travel grows both here and around the world. Is how does this affect communities and how those impacts can be minimized? So net zero aviation is a important and wide open innovation opportunity for the energy innovation community that I would encourage you all to look at and partner with the federal government and companies to help solve. So this one is a big one, right? So remember, we started with 5. I know some of the professors in the room sometimes will give you kind of like a question with 5 parts, right? And everybody gets upset with that. That's what this one kind of is. So industrial products and fuels for a net zero circular economy. It's a big portion of what we're trying to do in the industrial sector. And so this is about solving what some people would have called the hard to abate sectors or the hard to decarbonize sectors. Why is it hard? It's hard because we haven't really tried, right? And so now it's time to try. And it's time for success, because we are going to find new ways to make materials and recycle those materials and have circularity in those materials. We're going to find new ways to alleviate vulnerabilities in the supply chain. We're going to find new ways to do advanced manufacturing with good paying jobs, both here and around the world. And we need to have these get to net zero. And the important piece here is it's wide open. And there's super great opportunities here for us to make a large dent across all the sectors that I was talking about before, in people's lives, in communities, in jobs, and in air pollution, to help an industrial economy grow, provide for the needs that we need both here and around the world, grow the types of jobs that are important, but also do this with less waste and growing, kind of working with nature instead of against it, and designing new materials and thinking about new ways to doing things. And so industrial products and fuels for a net zero circular economy is this big thrust that we're trying to advance as part of this game changer framework. And so the last one you may be surprised about, So the last one I know that Professor Jaina, as a physicist, is excited about. I am excited. I'm a civil engineer. Even I am excited about fusion. And let me tell you why. It is just from a purely science perspective, it's wondrous, right? It's just the idea that we can capture and create a star inside of a bottle here on Earth is just a marvel of science and progress. And so fusion energy at scale is one of our game changers, because remember, we're thinking about the long term. We're thinking about what is the investments that need to be put in place now so that we have innovation in the 2030s, the 2040s, and beyond, in the 2080s. And so we need to be always advancing science and engineering progress to ensure our net zero goals are met, but also the world doesn't stop in 2050. We have to ensure the types of technologies that are power our world for a long time to come. And so fusion has been going through a renaissance. and has had lots of private investment and capital. There's been major breakthroughs. You may have heard from the one at the Lawrence Livermore Laboratory last year, but there were a series of breakthroughs before. Some of them have been enabled by the Department of Energy's ARPA-E program. And so investments in early stage and very early stage technologies have yielded really positive results. And so we don't have a power plant yet, but there are opportunities to learn and grow along the way so that we can get there. And the president launched a bold decadal vision for commercial fusion energy last year at a summit. It was the White House Summit on Fusion Energy hosted by our office and the Department of Energy. And that the first White House Summit on Fusion Energy is something that we brought together people from around the country to figure out what's necessary to advance this really game-changing energy source with near limitless fuel. Now, we also, while I'm talking about our summits, because these summits will tell you kind of what we're trying to focus on in advance. We had a summit on electrification. So we had the first White House Summit on electrification. We had the first White House Summit on climate and communities, and thinking about how communities like Richmond can work together with universities to advance not just climate research, but net zero deployment. So how can VCU and other universities help their communities learn what it looks like to be a net zero community? And then we had a White House roundtable on circular economy. So one of our functions at OSTP is to bring these communities together, help share and lay out a vision and get to where we need to go. And so on fusion energy, the president, the Department of Energy, and the White House are excited about the opportunities that we're advancing in fusion. So this is where we're going to need your all's help. Typically, we heard from Professor Whittingham the way that lithium-ion batteries were discovered, and that there was IP generated, there was prototypes, it went in different directions, amazing discoveries that we rely on every day right now. A lot of times, and we looked at this and others have looked at this as well, is in the history of technology development and commercialization, things take a long time. That battery was kind of first discovered decades ago. And now we're seeing batteries that are viable and cheap enough to be in cars and on the grid. And so the basic science, the discovery-based science that many of you all are doing every day that is critical to the future of humanity is absolutely essential. As that basic science grows the pool of knowledge, there's maybe a proof of concept emerges, and then technology development, and then there's regulatory issues and market frameworks. All of these things take a long time because they're typically done in series. And we do not have 70 years to do the next generation of energy innovations that I'm calling for here. We have much shorter time. So again, how do we make something go faster when it's in series? We're going to put something in parallel, and we're going to do parallel processing. So just like a computer will take a big task and divide it up amongst several processors and do it different parts of the task so that they can come back together, we're going to need to do basic research, innovation, engineering, proof of concept, policy development, regulatory environment, all kind of at the same time, so that one piece is feeding off another piece. And so with maybe the regulatory environment says, what would be safer is if you did something like this, and then engineering and science can go back and fix it that way. It does not have to be a linear process of innovation. We can have this be more of a parallel process so that we can get to the market commercialization of these exciting technologies and integrations much, much faster. So 10 years, maybe on the short end, we'll give you 15. That's fine. We can, it's from discovery to scale up. But what we need to do is we know that a linear process is going to take 70 years is not viable for our current climate scale. So Dr. Prabhakar, who's the head of the Office of Science and Technology Policy and a cabinet secretary, she likes to talk about doing things that the climate notices and doing things at the speed and scale where the climate notices. And her vision has infused all the things that we're trying to do here is that speed with care, speed with inclusion, speed with equity, and speed with scale is how we're going to need to approach this and tackle the climate crisis. And so there's roles and responsibilities for the energy innovation community, the social science community, law, business, finance, trades, construction. There are opportunities in the clean energy economy for everyone. And we have a vision that we hope that we can partner with the rest of this community on. So how do we align our energy transition goals, right? And so this is all the things that need to get done. We need to get to zero, right? We need to get to net zero, and we need to do that no later than 2050. We have to do that by building broad coalitions and creating good paying jobs. We have to advance environmental justice. The president signed an environmental justice executive order 2 weeks ago. We have to clean up legacy pollution. There's opportunities here for new ways in designing pollution. As this world advances and energy becomes more and more intertwined in our daily lives, we need to make sure that we have energy security and that we're increasing our economic competitiveness and maintaining our relationships with our partners and allies. So we've just now added to your list of things that need to get done, all within, let's call it 25 years. I am very confident of the innovators in this room and around the country that can work with the research community, with our wonderful national lab system, with the university system, community college, and with our K-12 education system to all row in the same direction of getting to a clean energy economy that is grown for everyone. And so I am excited to be here. Congratulations on the opening of this wonderful center. I and the rest of the White House are looking forward to interacting with all of you on this journey. And we'll see you back next year here, hopefully with some new innovations. Thank you so much for having me. Appreciate it. I think there's some questions, and Professor Jenny, do you want me just to take the questions? I'm happy to do whatever you'd like me to do.
Please go ahead. Seem capable of fielding your own questions.
Okay, well, that's dangerous. We'll see what happens.
And microphone.
I'll just stay up. I'll stay up. Yeah, that's fine. Yes.
Yeah, one of the things, thank you for the great insights. And again, I'm a great admirer for things that are doing. And most of them are quiet revolution, like introducing heat pumps in the houses, that can, I'm just giving an example, electric vehicles. But my question is, one of the things, electrification of cars is batteries. Do we have supply of raw materials like cobalt, nickel to convert whatever the target of 2030 is? Because China has cornered all the cobalt in Congo.
So the question,
how is being handled?
So the question,
the purpose, the raw materials need for batteries.
the question is, what does the supply chain for raw materials look like for electrification of vehicles, and how do we meet those challenges in the very near and mid and long term? So the president and the White House initiated a process of understanding the supply chain for critical and raw materials. Department of Energy had a big lead role in that, and has produced a series of reports and actions that the administration is taking on ensuring that we have the raw materials necessary for the clean energy transition. On electric vehicle batteries especially, there are new chemistries that have been developed that don't rely on these some of these more harder to get minerals. There's also the opportunities for a more circular economy. So I believe that we have in the near term a plan in place to ensure that we have access to the materials that are necessary, and that innovation that we see in new batteries like lithium iron phosphate, and we've heard just of this past month, we heard innovations in sodium ion batteries. We should not assume that the batteries of 2038 or 2035 look like the batteries of 2023. And so I am excited about the possibility of broad innovation when the world starts focusing on electrification of vehicles, on what battery chemistries, battery materials, and battery costs start to look like.
Other questions, Crosby?
So this was very informative and useful. Thank you for a very, very elaborate talk. So my question is, as we move along with our net zero plans and all of this, what's the strategy for engaging the industry because they are the key people who are going to be deployed. So from the both policy side and from the implemented strategy side, just would like to know.
They're part of the administration's engagement from the beginning of this administration has been with our clean energy industry innovators. And so you're absolutely right that the electric vehicle manufacturers, the battery manufacturers, the steel producers, the cement factories, all of these folks who are day in, day out delivering the types of products that we all rely on are key partners in advancing this clean energy transition. But I'll also add a partnership with labor. And so making sure that that communities around the country have access and opportunities for good paying jobs is key. So this is going to be a partnership with industry. It's going to be a partnership with labor. It's going to be a partnership with research. It's going to be a partnership with education. And so we know, as much as I would love to write papers and let them sit there, that's what I used to do, and I still like to do that, by the way. Happy to write some paper. I want to make sure that the stuff in those papers gets to a device, gets to the things that we want. And so a partnership with the folks that are doing things on the ground has been our operating tempo from the beginning.
Thank you for the talk. With regards to nuclear fusion, having a pilot plant on the grid in 10 years is certainly an admirable goal. What's your budget plan for that?
So if you look at the president's budget request for this coming year, there is a large increase in the budget for fusion that has milestone program requirements and opportunities and other materials and research areas. Obviously, to advance any type of new technology is going to require resources, and we are taking the appropriate steps to make sure that we're growing these fields in a way that is commensurate with the challenge. Now, it's important that in fusion, especially, the money from the public sector catalyzes all kinds of investment from the private sector. So our public sector budget has grown. And what that has done is increased and poured new attention into fusion from the private sector. So between the public sector and the private sector, I'm confident that there will be resources to make sure that we're advancing towards the president's goal.
Hi there, I'm Damian Pitt. I'm Associate Director of this Institute and also Professor of Urban Planning here at VCU. So first of all, thank you for the great presentation and the the comprehensive strategy that this administration is taking towards the clean energy transition. But from the perspective of my field, there are a couple of big concerns, or like what I would consider omissions in the strategy related to transportation. First of all, I'm not seeing the commitment to reducing vehicle energy demand in the first place, right? So as we, and as it relates to the transition to electric vehicles, we also should be reducing vehicle miles traveled, reducing automobile dependency through better mass transit, intercity rail, et cetera, which we've not made much progress on in this country in many decades. And the second piece is with the EVs themselves. Like, we have this very complex system for determining which types of vehicles gets tax credits and which type of manufacturers get tax credits. And the end result of that is that it's almost entirely large, expensive, many of which would be considered like luxury vehicles that are being incentivized now. The one EV that's made in America that is small and affordable is the Chevy Bolt, and we learned yesterday that that's not going to be made anymore. So how can we better use, focusing on that second part of the question there, that second concern, how can we, what are we going to do to incentivize smaller, more affordable EVs that are also safer for pedestrians? We have a increasing number of pedestrian fatalities in this country, and the transition to large, heavy EVs is a major concern there as well.
Thank you so much for that super important point and question. 100% absolutely, we need safe streets for everyone. We need communities that kids can feel safe playing outside in the streets, and opportunities that increase roadway safety, not just for drivers, although that's super important, but for cyclists, pedestrians, and everyone else. In the bipartisan infrastructure law, there was the largest investment in passenger rail and public transit since the creation of Amtrak. So the president's actions have demonstrated the commitment to public transit and to passenger rail. We need to make sure that our strategy for transportation is electrification plus. So there's not going to be one thing that is going to solve this challenge. It's a lot of the different elements that you listed to make sure that we get net zero, safe, equitable mobility and access for everyone.
What about smaller EVs?
For smaller EVs, there are opportunities for, so let me put it in the personal. Where my family lives in Pittsburgh, there are hills everywhere. And so I would not bike to work because it was uphill both ways. But I got an e-bike, and it basically changed the way that I use these short trips. Most of the trips, as you know, that people make in the country and in many parts of the country are fewer than a couple miles. And so there are opportunities for shifting from car to public transit, shifting from car to e-bike, and finding ways to make our vehicles safer for both pedestrians and other drivers. So absolutely agree with you that this is a multi-pronged strategy that's necessary.
We have time for one final question in our final 2 minutes.
I once again would like to thank you for your many comments. I was very interested in some of the things you said about the impact of where this goes. And I was looking at our international cooperation. For example, are we working with Africa, which certainly would be the kind of destination where they did little to cause the effects of global warming, but in fact are suffering the impact. And there's a small second part to it, which is how would you be collaborating with people whose first language is not English, but perhaps might be French? Or in Africa, the education systems, you have about 40% of them that are in French. So I'm just wondering about the international collaboration and opportunities to do that.
That's a super important question. While I'll defer the biggest part of that to my colleagues at the State Department and Secretary Kerry's Special Envoy for Climate Change office that works hand in hand with our international partners and allies around the world, I will say that there is an opportunity and indeed a responsibility for the United States to lead on clean energy technologies because of the emissions that we have generated and the emissions that we're currently generating. And so we can lead by example, and that's what the administration is doing, both in the government and in the private sector, and encouraging through the private sector. So the administration is committed to ensuring that there is partnerships with our partners and allies around the world to make sure that everyone has an opportunity in a clean energy economy.
I know you will all join me in thanking our wonderful speakers. So we do have a call, as you said at the start, we do have an opportunity of a break here for 30 minutes, but we hope to come back for the next session at 10:30.
How are you doing? Glad to be here.
If you're speaking today, please email or give me your flash drives for your presentation.
Next speaker.
Hey, so we found out that we can technically do it, but then we don't have.
And I want to make sure that you all are.
I mean, the mic, is this being broadcasted?
Yeah, but we weren't supposed to record. We're just recording.
Oh, okay.
And we will be-
But if I speak loud enough, or it's not.
It's not, the mic's not. Oh, we just won't pick it up. We tried.
All right, it's okay. I'm going to, I have no other choice. Really. Yeah, that's good. You can try. Good morning, everyone. Good morning, everyone.
Good morning, everyone. We're about to start the second session. Thank you so much. My name is Gary Tepper. I'm the interim dean of the College of Engineering here at VCU, and it's my pleasure to host the second morning session. The topic of the session is Frontiers in Clean Energy Generation. The format is there will be 3 speakers in the session. Each will speak for approximately 25 minutes and leaving about 5 minutes for questions. All speaker bios for the entire symposium are online, so I'm not going to spend a lot of time giving long introductions. I'm just going to launch into the introducing our first speaker, my boss. Provost Soteropoulos is our first speaker. He's the provost and senior vice president for academic affairs here at VCU, and also an international expert on fluid mechanics and computational methods applied to various areas, including clean energy generation. So without further ado, I'll turn it over to Provost Soteropoulos.
Right. Thank you. So what do I do here with screen share? Why isn't my presentation? Let's see. It was share. Maybe I have to share again. Okay, that's fine. All right. Do I need to use the mic? Or
No, you're fine.
I'm fine. All right. Okay. Thank you very much, Gary, and thank you all for being here. And special thanks to Professor Puru Jena for his energy, vision, and inspiration. Actually, he's the one who is the driver behind this institute that has brought a big cross-section of the VCU community together. And also he has been the driving force for organizing this great symposium. So I'm really grateful for all the energy and enthusiasm here. Now, as I was asked to speak here, it's interesting because it turns out that my entire career has been shaped by doing research in a number of these areas, right? And as Gary mentioned, my research background is in the area of fluid mechanics, specifically into the area of using computer models in the simplest terms to create digital twins of flow environments to understand basic physics, but also do things like solve big engineering problems. And I have focused a big part of my career actually into developing computational tools for supporting the development and optimization of wind and water energy resources. As I was putting this presentation, and by that, by the way, I mean hydropower, wind power, tidal, and wave energy, right? These are all technologies that use fluids, whether it is in the ocean or in the atmosphere, to extract energy in different types of ways. And so as I was putting this presentation together, it occurred to me that, I have not talked about hydropower for a very long time, but the very first project that I got in 1995, when I started my academic career as an assistant professor at Georgia Tech, was by Voith Hydro, a major hydro turbine manufacturer, to develop computational tools to understand the turbulent flow environment within a power plant, to really understand what it means from the standpoint of fish that are passing through the power plant, to assess the environmental potential implications of hydropower, right? And then this continued on, and my more recent work is in tidal and wind energy. So I have kind of, through my career, I've worked in all this. What I'll do in this talk is I'm going to highlight some key areas of where we are and what are the future opportunities in all these 3 areas. And I'll also touch upon my own work to drive the point how important is research that happens in universities such as VCU in partnership with industry, with government labs, with federal funding agencies, really to advance understanding and develop the tools that allow us to be now in a position to think of how we can incorporate renewable energy generation from wind and water resources into a power grid toward the future of electrifying our infrastructure. I mean, producing our electricity from net zero renewable energy resources. So looking back, these three areas of hydro, wind, tidal, wave, which is they have played different roles in the history of renewable energy generation in the US. Of course, hydropower is the most established and traditional, right? It's for over 100 years, actually, hydropower has been for a long period of time the only renewable energy generation in the US, right? And you can see this in this graph that really highlights how over the years up until the early 90s, in fact, hydropower was the main driver there. And as we go into the 2000s now, the green part there, which is wind, begins to grow, right? But hydropower is still a very important contributor in renewable energy generation. And the point I would like to make, each of these types of technologies have different potential. They can make different impact to producing renewable electricity. For instance, wind has the potential, if it's developed 100%, to power the entire US base, right? I mean, whether we can do it and how much is feasible, it's another story. Hydropower, on the other hand, there is significant potential for energy generation, but it is also but there are a lot of issues and constraints, right? And I don't expect that there's going to be significant development of new hydropower beyond what's already developed, but it could be used in very creative and innovative ways to integrate it into the power grid, as we'll talk about. Tidal energy also has the potential to generate up to 10% of electricity. You might say small, but tidal energy is very predictable, though. So it has a lot of value when you're talking about the future of a power grid that integrates renewables at very high penetration level. And that's what this slide is trying to illustrate there. This is taken from, it's a couple of days, one in 2 different months in 2012 and 2020 from Germany. And of course, what you see in about 10 years ago, you had a grid where a lot of conventional power resources, right, which are predictable, they provide base load, you can control, you can bring them on and off in a very on demand as needed. But now, as we go into what it is shown for the more recent picture of the power demands in Germany, with deep renewables penetration, right? There's a lot of variability, there's a lot of intermittency there. So you have to change completely the approach that you manage the grid, right? You need flexible backup and not base load. You don't need to operate like a gas power plant, a coal power plant constantly throughout the time. You need to bring it on and off as needed and ultimately phase it out completely and think of storage and so on. So these are very different paradigms. And that picture is very important because it really talks about the need to develop a series of renewable energy resources and use them in different creative ways in the power grid, right? So let's talk a little bit about hydropower. You know, you see at the lower image here to your left what a hydropower plant looks like. Essentially, you build a dam that impounds water in a reservoir that sits at a higher elevation than the river downstream, right? And you allow the water to flow through the power plant, and you convert potential energy into kinetic energy by spinning a turbine, all right? And that is connected to a generator that produces electricity, right? So that's pretty much what happens in a power plant. Now, there are a lot of issues, of course, environmental issues that essentially have created some difficulties for hydropower, because the moment you impound water into a reservoir, you get a lot of the sediments which are rich in nutrients to be stored there for very long times, which means you deplete the downstream water from these sediments, right? From a lot of important nutrients that impacts fisheries, water quality, and so on, right? There are also other issues where as you store water in the reservoir and the power plant tends to draw from the lower levels of the reservoir, that water, certainly in certain months of the year when the water is, when you have hotter water on top and colder water at the bottom and there's not enough mixing, you draw from lower levels of the reservoir water that doesn't have much dissolved oxygen because it's been sitting there. As a result, again, you feed the the rivers downstream with, you create water quality issues. And of course, the bigger issue there is the fish passage issue in rivers, like especially in the Pacific Northwest, where you have salmon that migrate from the Atlantic upstream and from upstream to spawn, and then from the spawning grounds back to the ocean. You know, they have to navigate these power plants, right? They have to go through or around and so on. So the early work I talked about was really to try to understand how to design fish-friendly hydropower turbines, right? And in fact, there is a lot of work that has been done in this field, and a lot of money that has been spent to develop very sophisticated systems that allow fish to bypass the power plant, right? To give them an opportunity to both move upstream or downstream without actually having to go through. There is a lot of work that has been done to improve the design of hydro turbines to make the flow environment friendlier to passing fish and so on. So I just want to bring to your attention this issue, because that's an important issue for hydropower, right? Now, the more recent and more exciting, perhaps, use of hydropower is not so much in the development of new hydropower, but in new uses of hydropower. And I think the most exciting area is thinking of hydropower as a giant water battery, right? Using pump storage technologies. So the concept is very simple. When you need energy, right? When the grid needs energy, you let the water flow from the reservoir to from the upper elevation over the reservoir to the downstream river, you produce energy. But when you actually, and you give that energy to the grid to satisfy the demand that you have. But when you are in the opposite situation, where you say you have a lot of renewables that are producing a lot of energy at a time, like wind, solar, and so on, when it is not needed, right? So you can use that electricity from the grid to run those turbines in a reverse mode, like a pump, and pump the water from downstream, from the lower elevation up into the reservoir and store it there. So now you take electric energy, convert it into kinetic energy in the pump, and you store it in terms of potential energy to use it whenever it's needed. In fact, this concept of giant water batteries, they've been developed right now. Switzerland, I think, recently, you may have read the news, they have developed in the Alps, actually, a major thing. And the great thing about this concept is you don't necessarily need a river. All you need is two lakes that are at different elevations, right? And you can take the water back and forth, right? So there are a lot of innovative ways as far as hydropower goes to contribute into our renewable energy grid. Moving on now to marine and hydrokinetic energy technologies, as collectively the term we use. Oops, I think I have a setting here in my presentation, which I forgot to change, so I might have to go back and forth. So this is about really extracting power from tides in rivers and streams, or waves, or a combination of the two, right? And there is a range of devices, really, especially this is the wave energy in particular, and tidal energy. There are all kinds of exotic concepts and devices, right? So when it comes to tidal energy, essentially, we're talking about turbines, like underwater wind turbines, pretty much, where you extract energy from the water current. But for waves, there are different types of concepts that have been developed and so on, right? My work there has focused on in the area of tidal energy, and I'll talk to you a little bit about this. There is considerable potential for producing energy, whether it is from tides or waves. And you can see in this map from NREL that a lot of the sites and the potential for wave energy generation of the coastal areas, but also in our riverine system, the Mississippi area here, a lot of potential for producing water, for producing power from streams and rivers and so on, right? Now, a big issue there is, it's one thing to do the theoretical resource has to do how much wind, how many waves we have, what's the intensity of waves, what's the intensity of the currents and streams and so on. Then there is the issue of technologically what we need to do in order to extract this. So from theoretical resource, you go to technical resource, and then you have to add the environmental considerations to see how much of this is practical, right? But it is an important, and that's an opportunity for research really right now that is happening, to try to understand how much of the available resources we are able to practically utilize and extract, right? But I see, as I said, a very important area there is a very important topic, especially for tidal energy, is its predictability. We know exactly when the tides come in and when they go out, right? So you know that maybe if you have 10% of power you can produce from tides, you know exactly when you can put it into the grid. That worth a lot of money for folks that have to optimize grid integration of renewables, right? It has very, very important value. So a little bit about tidal energy, some of the issues that I have worked in my career is looking at device hydrodynamics, right? How you improve the design of devices to be able to maximize energy extraction, and also look at how they interact with ambient flows, with sediments, how multiple devices interact with each other. You have to be concerned about potential impacts of these devices in the geomorphology of the rivers, in the shape. Are they causing extra erosion? Are they causing extra deposition? Do they change the ecosystem in which they operate? And of course, last but not least, is to really look at potential device-biota interactions. What does it mean from fish and so on? And it turns out that when it comes to fish and so on, this is not a significant effect. These turbines are rotating fairly slowly and so on. But this is the totality of the issues that are at the forefront of a lot of the research that is going on. So I'll tell you about a specific project that I had the great opportunity to work early on in my career. I don't know how many of you have seen this, but there's this company called Verdant Power that was quite pioneering. They've been at it for decades right now to try to develop the first grid-connected tidal energy plant in New York City's East River. Okay. And in fact, you see, this is a couple of years ago when they have been into the river. They've done a lot of studies, a lot of environmental studies. The East River is an ideal environment because it doesn't have sediments, maybe some dead bodies that float from New York City in there, who knows what. But really, it's not an issue as far as habitat is concerned. And it was an important issue for them to be able to get approval to even try it there, right? Because the kind of the ecological ecosystem impacts were fairly minimal there. So the idea is to develop these plans of putting turbines in this tri-frame. So you have this triangular base and 3 turbines mounted there. You can drop them into the river, drop several of them, create a plant, right? So we have been working with this company from a long time ago, since I was at the University of Minnesota. In fact, we did some of the first work in this area before any turbines went into the river. And what we did is we took the bathymetry of the East River, we create a digital terrain, a digital river, right? And with our computational tools, we were able to simulate how turbines will operate in that river environment, right? And we have done this way before these turbines went into the water. So our work there, it's kind of led the way and provided a lot of important guidance, right? And right now there's a lot more research happening in there. So this is an example, for instance, for a numerical simulation of this tri-frame. Red is high water speeds, blue is lower water as the turbines extract water from power from the tide and so on. And what we have done here, again, this is lots of work that we have done over the years with my students and postdocs. So this is a digital twin of the East River, right? In which before the turbines even went into the water, as a matter of fact, I don't think a plant like this exists right now. It exists in our computer simulations only, all right? But this was funded with a lot of money from NSF, ERE, the Department of Energy, and industry. So you see here the power of computational tools. We can build these models in high performance supercomputers and really begin to understand how much energy they will extract, and also begin to understand, to figure out how to optimize their arrangement and their operation, right? So very, very important. I mean, computational models can be very, very, in fact, could drive the development, and they are driving the development of a lot of these resources. Now, another important area that we have done computationally is what happens if we want to deploy these turbines in sandy environments, right? They have never been deployed. They don't even have permission to deploy them there, right? But in a computer model, we can do really whatever we want. So we develop computational models that we take into account both the flow of the water and the motion of sediment, right? So what you see here, that brown surface is actually the turbine begins to operate, but the sediment is able to move, right? So so that's why you see the deformation. There is erosion behind the turbine and deposition here. And then here you see both the flow and the sediment together. These first computations actually helped design and inspire a major experimental study that was done by my colleagues and myself at the University of Minnesota in a big flume that we had there. Most of the work was done in my earlier life when I was doing research. A lot of it was done at the University of Minnesota. That was before I went down to the dark side of being provost and all the stuff, right? That was, but this was a pretty landmark study in the sense that we were able to create in a big flume that is available at the University of Minnesota, a power plant of tidal turbines with a mobile bed. The problem is, if you have a big flood, will these turbines actually be covered by sediments? Okay, fundamental question that nobody had ever been able to answer. And it turns out they will not. And the reason is because the turbine has its own self-defense mechanism, which I don't have time to talk about this now, but you saw it in the previous slide, essentially, that as the turbine operates, it increases the shear stress and it creates erosion. So the turbine acts to clean the sediment locally and allowing for these dunes to pass through. If you have the same flood and the same sediment motion and the turbines are not extracting energy, they get covered right away. But the moment you allow them to extract, so this was some pioneering work that actually made it to the cover of Nature Energy, because for the first time it showed that actually there is potential for extracting energy from sandy rivers, really, and the environmental issues. And this is an example, right, how computational experimental work in universities now, they provide companies with the background they need to do the regulatory approvals that they need in order to be able to do this. We have real science that can inform decisions, right? So the last part that I want to talk about, the remaining of my talk and the bigger part of my talk, is about wind power, of course, the era of wind power. And this is actually work that I started when it was in 2016, 17, 18, I think they were, right? Or 2008, I'm talking about. What I'm talking about? It's a long time ago, right. So the reason it's a great pleasure to have in the audience here, Jose Zayas, who at the time, this was when the Obama administration issued the stimulus, big funding, and set the very first goal for the US, right? 20% by 2020, right? 2030, right? And Jose was at the Sandia National Lab leading the renewable energy programs at the time. I had submitted a proposal. We put together a big industry consortium. We submitted a grant to the DOE while I was at the University of Minnesota. And Jose was part of the review team. So he came and gave me a lot of hard time at the time because frankly, a lot of the things was vision. We didn't quite know which direction we're going, but neither did anybody else really. It was so early on, right? But I was very fortunate to be able to get that funding that kind of led to a whole new, up to essentially some of the work that I will show you right now. And later, of course, when Jose moved to ERE, we worked together there for many other projects and so on. So I'm really glad that kind of we come full circle here. And so first of all, at the highest level, there is enough offshore power potential to power the entire world. And this graph is interesting because it shows how little of the ocean, this is the blue areas, will have to be developed, right, to produce enough energy. Of course, not all of these areas can be developed because they have to be, it's not enough to produce the energy, it has to be accessible to the grid, right? And there's no doubt that wind alone is not going to do it, right? We're going to have to have a mix of technologies, but really wind has huge potential, right? So, but if we really want to move to reach net zero by 2050, we have to dramatically accelerate. There's a lot of progress that has been made in the US and of course in other countries in the world in developing wind energy in the last 10, 15 years. But this pace has to accelerate dramatically if we want to get to the 2050 net zero goal. How do we do this? Turbines are getting bigger and bigger and bigger. That's how we do this. That the three-bladed turbine technology has dominated. It's very mature. It's very clear, even though there's a lot of work about exotic designs, turbines that can be deployed up higher up in the atmosphere and extract energy. The thing is, it's very important for the turbine to be as big as possible because the area of the turbine plays a big role into how much power it can generate, right? And it has to be as higher up from the ground or the ocean surface as possible, because closer to the ground, you have what's called the atmospheric boundary layer where the velocities of the wind are lower, right? Lower potential or lower energy there availability. So the higher you go, the more potential you have to extract more energy, right? So and you see the bigger the turbines, they go off land and they get into the ocean, right? Because such big turbines, they cannot be close to any urban area or so on. They create all kinds of issues, right? But right now we are looking into 10, 15 megawatt turbines down the road, really, which are massive structures. You can see an Airbus 380 really in relation to this. These are mega structures with huge, huge blades. Aeroelasticity, loads, are these blades going to break, materials for how you manufacture them and so on. There's a whole host of issues, right? My area of research, being fluids, is really how turbines interact in an atmospheric setting with many other turbines. And that's a very famous picture in wind energy research. It's the Hornsref wind farm, a day of low clouds in Denmark. Low clouds, they kind of visualized what happens in a wind farm, right? And you can see here that not all turbines are created equal, right? And the first row of turbines here have quite different flow environment, but the effect they have in the flow changes drastically the environment that the subsequent turbines, right? So the important thing here is that it doesn't, if our objective is to produce wind power at big scale, wind farms produce this, and we need to really think about what happens at the wind farm scale, right? So we need to do more work, even though the costs have come down substantially, but we need to more work to minimize wind plant energy losses and structural loads that are really related to the flow environment, right? We need to incorporate ways, advanced controls. And I'll talk a little bit about this, the way we control the blades, right, in response to the flow. These things are not necessarily incorporated in the design that we do right now to do this, what is called control co-design. And ultimately, we also need predictive computational models of wind plant performance across a range of timescales. The timescale piece is very important here, right? Because if you are a developer and you want to develop a new site and you want to get an idea of your annual power output, right? Then you can predict things at the annual scale. But if you want to integrate a specific wind plant into the grid, you need to know how much is going to produce an hour before, a day before. Right? The shorter the time scale, the more difficult it becomes to produce accurately, right? And different types of computational tools that are needed. So there's a lot of work here and opportunity for computational science. Ultimately, we need to have a paradigm, and this has already been happening, shift in research. Walk away from one turbine. I mean, it doesn't really matter. I mean, it doesn't matter, but these turbines, their technologies, they're very sophisticated machines. The real important thing is how they operate in multi-turbine wind plant environments, right? The objective is not to optimize the performance of one turbine, but to optimize the performance of the entire plant. Sometimes one turbine might need to be sacrificed over the social good, the collective good, right? And do this in complex terrains if we're talking about onshore, or ocean environments if we're talking about offshore, right? So there is a tremendous potential there for computational science to put together data with computational models to really be able to optimize the wind farms of the future. And I'll show you some of the work, this project actually that I mentioned before that Jose was really instrumental for us to get at the University of Minnesota. At the center of this was building an actual 2.5 megawatt wind turbine that could be used as a field scale laboratory. We built miniature turbines in wind tunnels, but we have never done anything to try to understand how turbines work at field scale, right? What the flow looks like. And in Minnesota, of course, it snows. So some of our students and faculty had this brilliant idea that, during a snowstorm, I mean, if you stand under a lamppost, right, you see the snowflakes, right? So if you have a camera and you make a video and you process individual snowflakes, you can compute the velocities of the flow field, right? So that we did at the turbine scale. And this is a facility now that is being used. This snow, using snow as a visualization means of the flow is very, very exciting. And so what happens, so this is, I don't know if you can see this very well, maybe you cannot see it in this screen, but yeah, it's unfortunate you can't, but so the lighting is not right. But what happens is, in very simple terms, as this turbine rotates, it creates this big spiral vortices, right? So when you cut with a light sheet in this course of these rotating spirals, the centrifugal force kicks the particles, snow particles out, and you see black spots there. All right. So there's a lot of science and analysis that has gone there. This was published in Nature. It was really, I believe it remains today the largest field scale experiment, actually, and it was funded with DOE funds that we started early on at that time. And that led now to computational models. We led to brand new physics that we wouldn't have any way of knowing unless we were able to do this experiment and combine with these computational tools, right? And of course, now moving from one term, so by having the ability to validate our computational tools with facilities like this, now we can expand and really look at what happens, try to virtually simulate entire wind turbines, right? So this is an example of the work that we did a few years ago with a major development in energy, where we got the data of a particular wind farm in the state of Washington, the Vantage wind farm. And we were able to build actually a digital terrain model of exactly what the terrain looked like. And then they have a wind farm installed there. You see these wind turbines. This was developed with simplified engineering design tools a number of years ago. But now we can set up simulations, right, of this specific wind farm, and you can actually see. So what you see here is just a slice at the hub height of the turbines, and the reason of this difference in the inflow is because of the mountains, right? You have different, these are all taken into account in the simulation. So the bottom line is, here's a turbine that is not producing much power at all, as opposed to a turbine that is there, right? I mean, the power of these tools is exactly this. If we now can, this wind farm has been developed and the data that is producing can be used to validate our models. But the idea is we have tools now that we can be predicted, right? And do this in advance, right? And we have done comparisons with data and so on. Similar tools are now, we have used these types of simulations. I talked about the Hornsrev wind farm earlier on. We can set up these pretty large scale simulations now, computer simulations, where we are looking at how these turbines perform and try to maximize the performance of the power plant's computation. Floating turbines is a new exciting technology that allows you to deploy turbines much further from the shore, right? And this is exciting and cutting edge, and a lot of work is happening there. With funding from DOE, we developed the first computational tool that can incorporate waves with wind and incorporate the dynamics, 6-degree of freedom dynamics of the floating structure, right? And now these tools can be used and are being used to really design these types of turbines. And last but not least, I want to tell you about the control systems, which I haven't talked about, because these turbines have very sophisticated controls. Typically, what they do is they pitch the 3 blades in response to the flow. This is called collective pitch control, right? And they do this when this is what the operating curve of a turbine looks like. Wind speed. As the wind speed increases, there is a particular speed when the turbine begins to extract energy. In this regime 2, you're trying to optimize energy generation. But then when the winds get really fast, then you get into survival mode. You don't want this to happen, right? And what happens in this case is the winds get so fast that these blades begin to bend, right? And at some point, the blade hits the tower and so on, right? So how do we do this? So for that, the industry is exploring ideas to individually pitch the blades, right? This technology has not been widely deployed, but we have developed computational tools that can do this individual pitch control. They can incorporate the aeroelasticity of the blades and hopefully, and what we are finding for this right now is that these new advanced ways to control the turbines, they reduce the bending moment significantly. This has significant implications in terms of how much you can, the envelope over which you can operate the turbine, right? And also they are reducing the tip deflection. You can actually, with controlling each blade individually, and the bigger the turbines become, the more important this becomes, because each blade, the diameter is so big that each blade experiences completely different part of the atmospheric boundary layer, right? I mean, so this is brand new cutting edge work really that actually shows the potential of this. A lot of implications for the cost of energy and so on there. And these computational tools again are paving the way. And the most exciting thing is that you can do all this without actually any effect on mean power generation. Right? So our computational work has shown all this. And now we're working with industry to really apply these tools to real wind farms, right? And the last thing I want to talk about is we have a unique opportunity right now with machine learning, and we're doing this, to use these high performance simulations that are very expensive, use them to train machine learning models that can do these predictions very efficiently. And we're getting some incredibly encouraging results right now, because remember what I said at the beginning, and that's my last slide really here, how important it is to do work how important it is to do predictions at different scales. These models they are very expensive, but if I want to predict what a particular wind plant will do a day ahead, I need to do something different. And machine learning informed with data that these simulations are producing provides a clear pathway for doing that. So thank you very much.
Maybe I have gone over my time.
Yeah, we're a little over, so I think we'll do, Farouk?
Fundamental turbines not fall apart like the heat.
I think the materials, I mean, the materials are quite optimized right now. There's a lot of progress that has been made in these materials, but I mean, improvements in composites and so on can always be made, right? I have to say, because I've seen, I don't know if you've seen an actual blade, how elastic these things are. It's just unbelievable. These massive blades, you can actually move them with your fingertips at the end. It's just very, very sophisticated from a material standpoint. Yeah.
Thank you so much. I think we're going to have to move to the next speaker. Are you loaded up or you need any help? So while he's loading it up, it's my pleasure to introduce our second speaker of the session, Professor Prashant Kamat of the University of Notre Dame. He has a much fancier title than that, but he's a distinguished professor with one of the most highly cited researchers in his field. He's going to give a talk entitled Transforming Next Generation Photovoltaics with Semiconductor Nanostructures. And I see you've got it loaded, so please help me welcome Dr. Prashant Kamat.
First of all, thank you for the introduction. And sorry, I'm used to the traveling, walking around, but I have to stand here. So anyway, thank you, Puru and ISEE for having this nice conversation from different disciplines. And one of the things they want me is cut down your science, but give a more broader picture. So I was also hoping to see more younger students. So that's how I steered this one. My original title was Transforming Next Generation Photovoltaics with Semiconductor Nanostructures, but it's more like reducing carbon footprint with the next generation photovoltaics. Okay, this is 50 years. What is it? Okay. Okay, 50 years back, right? Long back. Nature had a nice editorial, okay? This is the most prominent magazine, right? And they have not retracted this yet. The reason is, that's what they said. In an entirely natural world, no doubt, one consequence of adding CO2 is by the exhaust of fossil fuel chimneys would be to increase the growth of plant life. They went on to say, among other things, this careful study shows the greenhouse effect is exaggerated. Okay. And then they say, oh, it's not a problem. It would be feasible to undo the damage simply by calling a halt to the rate at which fossil fuels are consumed. Right? 1971, driven by fossil fuel industries. And they have not retracted it yet. Okay, but we knew it. The Arrhenius in 1896, he had a paper telling us on the influence of carbonic acid. He called CO2 as carbonic acid. And he states that it is a greenhouse gas, right? So that's what it does. And now, okay, this is what we have. If you go to the NASA site, carbon dioxide is 420 and our temperature is 1.1 degrees. Arctic sea ice is melting. Sea level has risen since 1993 is about 4 inches. It is increasing 3.4 millimeter per year. Okay, you can see in the North Carolina beach, these houses getting washed away into the sea, just float into the sea, right? That's videos. And this is the reality, right? All the politicians around the world get together and say, yeah, this is a problem. We need to do it, right? See, this is when 1972 we started. Then the first IPCC, UN Kyoto Protocol, Copenhagen, Paris Agreement, Glasgow. But see, the carbon dioxide is increasing. It's not even changing the slope. It is growing exponentially. This is the reality. And this is what the Glasgow, Scotland meeting said was, this is the current emission. This is what we are pledging. To get to 1.5 degrees by 2030, we need this one. China, this is still slight less, but nowhere close. US done a good job, but still it is more than what it is. India has, in fact, increased. So this is the reality of the world, between what is pledged and what is required in the CO2 reduction. Okay, so again, these are the carbon emissions from various countries, and you know how it can reduce, right? CO2. Okay, but the good news is the coal has gone down. Natural gas has taken its place, and at the same time, renewable has gone. Around 2020, we crossed over, and we still continue that trend in 2022. Again, this is from EIA, again, the government side. Okay, now we know that renewable energy has taken off. Even the utility companies are embracing it and then trying to work with the people. They protested for a long time, but now they see how to put wind farms or solar farms into the grid system and doing it. But how did the renewable energy came into play, right? Just to give, I was hoping some students, I will give you some history, but anyway, this is the first time, 1973, when the OPEC oil crisis, because of this war between Egypt and Israel, the Middle East countries said, no, we will not give you oil. There is an oil crisis. There is a line for gasolines, and everybody was freaked out. And that's the first time people said, we need an alternate energy other than fossil fuels, right? So that's what it is. And you can see here, that's the solar energy. And this is the New York Times article from 1975. Artificial leaf helps in photosynthesis study. Joe Katz from Argonne, okay, he was working on it. So it tells you that we have been thinking about it for a long time, renewable energy. And the credit goes to Jimmy Carter, okay? We don't give him enough credit. Washington Post recently had an article, the president who tried to save the planet. He brought in efficiency. He asked people to wear sweaters, roll over the thermostats. Even there's another article, they say the efficiencies, the refrigeration, they're now 5 times more efficient than what it was in 1970s, but they're twice the capacity. We have now heat pumps. So all this, I don't know what happened. I can see here it is fine, but, okay. He created national lab, SERI, Solar Energy Research Institute. That is the last national lab done in a thing. And today it is one of the leading institutions in the world promoting renewable energy. Guess what? Next 4 presidents, Reagan, Clinton, Senior Bush, George W. Bush, all promoted fossil fuels. When I'm doing research in 80s and 90s, I couldn't use the word solar energy. I have to use photo-induced processes. It was turned down. People in the back audiences, dream on, it will never become. Okay, so this is how we got the lost opportunity. 3 decades of lost opportunities. Imagine if we continue with the same slope. Okay, but good news. In the morning, we heard from Costas talking about the 2 major transitions. One is in batteries, and another is COVID related to vaccines development, other things. For me, the major 3 transformation that happened in the last decade, 10 years back, the society doesn't see it. One is the surge of solar and wind as a cheaper alternative. The price drop has made it possible. Same way storage batteries, drop in prices have made, now we are talking about grid storage. 10 years back, we didn't talk about it, right? So the most important thing I find the success story is LED lighting. Imagine about 10 years back, even about when they asked to change the incandescent bulb with the CFL, all the politicians were just jumping around and saying, no, I like those yellow lights. They were all heat bulbs, right? But there was a quiet revolution. Now LED bulbs are there, and you go to the store, the incandescent bulbs, even if somebody gives you free, people are not picking it up, right? So this is to me, that is one of the reasons why the demand dropped down in the lighting thing, because of these are 70 to 75% efficient versus what used to be 5% efficient in your incandescent bulb. So again, these things are good. It's happening quietly, the revolution, and people are getting used to it. So people know the value of LEDs now. Okay, the cost of electricity from renewables is cheaper in all these things. So it is competing, and the renewables are going to play a major role. But we always think photovoltaics and nuclear as green source of energy, right? Because it doesn't produce carbon dioxide. But they themselves have a carbon footprint. Okay, this is from Nature Energy article, and they calculated life cycle greenhouse gas emissions. For coal, about 10% of the energy it produces is, again, we use it, but it is carbon footprint. For nuclear is almost half of it. Surprisingly, you can go and try to find out carbon footprint from nuclear. There is no information on any government website. It could, people say it could be 5 years to 20 years. That means because you have to get the ore, you have to concentrate, you have to enrich. Although the palette is small, the energy required to enrich is much higher. On the other end, solar is still half of what other things are wind. So this is the carbon footprint. Okay, so wind and solar perform even better with 2% and 4% respectively. This was an article published earlier by a group of Stanford. He says, energy balance of photovoltaics industry is the PV industry and net electricity producer. The reason is to make these photovoltaic panels, you need electricity. The rapid demand in photovoltaic such that it is consuming more energy than the existing photovoltaic panels can deliver. Okay, eventually they say, I don't know, 2025 or so, they will balance it out. That means the existing PV can support in terms of production of PVs. So the carbon footprint is there. So that's what the PV single wafer technology. You want high efficiency, there's a more carbon footprint. On the other hand, these thin film solar cells like cadmium telluride, which is done by First Solar, by the way, has much lower carbon footprint than the silicon. just take silicon, how much energy it needs. We start from sand. We need to have this high temperature melting and reduction process. We use carbon to reduce it, right? To make this polysilicon. From there, we have to melt it and seed it and make the rod. You purify it and then you dope it, clean rooms, and then you make PV. So this is the carbon footprint for silicon manufacturing. You take SiO2, they call it the carbothermal reduction, metallurgical SI, high temperature refining, and then crystal growth. So that's what it is, melting. And these are the giant crucibles where they pull it out, the rods, and to make the refining metal silicon. You can see here, every step has a lot of carbon footprint. So that's where we have it. And cutting the cord on the existing sand to silicon chemistries and realizing new, more efficient and less intensive process would facilitate rapid proliferation of silicon photovoltaics and decrease. So this is where we also should focus on, not just putting PV panels. What are the alternate ones? So this is where the semiconductor nanostructures come into it. Because they are solution processable, low temperature, ambient cooling, benchtop technology. You can make reel to reel, just run it continuously, and low energy demand for production and hence lower carbon footprint. Even there was an article saying that you can take these components and manufacture them on the moon if you have, I don't know why, but the NASA, they are working on it too. Anyway, so how can semiconductor nanostructures can play a role in decreasing carbon? Okay, this is to me, is one of the major turning point in nanotechnology or making semiconductor quantum dots. This is Munji Bhavandi from MIT. They published in 1993. Okay, Nature wouldn't have published this paper because it was a synthesis paper. But they made these quantum dots by chemical method. In a matter of less than an hour, they can make even kilogram quantities. And they can tune in the size, whatever size you want. This is the beauty of chemistry. So there is alternate ways of making same kind of semiconductor. And today, if you are watching TV, all quantum dots, indium phosphide is there on your TV. Okay, so it's a practical thing. But that is set the course. And then now we are making even perovskite nanocrystals where you can change things, you can make different nanocrystals. And just by changing the halide composition, you can say chloride, bromide, iodide, the band gap varies and you can tune the entire thing. They are very nice crystal structures and very uniform size. This is early on, we got into this, what we call quantum dot solar cells. And then we showed that same quantization effects we can see in the photo response. And again, we did a lot of studies in that one. I'm not going to go into detail, but what happened next is these are the things, success stories. Again, these are some kind of a semiconductor nanostructures or thin film technology involved. Today, I started with dye-sensitized solar cells with 13% efficiency currently, solid state and ETA, extremely thin absorber cell, they called it. That's around 18%, organic PV, again, same thing. And the perovskite solar cells that came out lately is about 25.7. The thickness of this one was 10 micron. This one is only less than a micron. That absorbs all the light. So now you see how much 10% of the materials you need compared to what you have here. So that is one of the things, advantage of these thin films, how they've done it. And again, these lead perovskites are lead halide complexes with a cation, like a spacer cation, cesium, methyl ammonium, formamidium. Those are the only three ones that can go inside and strain the structure to give you that perovskite structure. And with that one, they have gone it, just to give an example, this is the conducting glass, that's the FTO. If you buy it, fluorine doped tin oxide, that's the crystalline structure. And you can see here the rest of the things you add is the same height as this FU. That's your cesium, methyl ammonium lead iodide, spiro, that's a whole conductor and a gold layer. And you can make these cells, characterize, and those things. So just to give you an idea of how simple it is to make it, and we make it. Now the problem is to compete in a commercial world. You may be having the best cell. Nobody wants to buy to replace if it is the same thing. The perovskite solar cells have same efficiency as silicon. But as a consumer, nobody wants to buy it. So what they are doing is if you cannot win the race, why not join the race? So people are thinking joining with silicon and adding a perovskite layer on the top of it. And then now you can absorb the high energy photons in this perovskite layer and whatever goes in silicon. Today, they have the latest report is 32%. So again, it is better than 2. Silicon is around 28%. This is about, maximum one, it's about 26, 27. This is 25. So now together they can get 32%. So that is a good news. So that's where it is going in that direction. Another nanostructures, they can be LEDs. Most of your LED bulbs have some kind of these phosphors because LEDs are typically blue LEDs and they need to get into white light. So that's why they put it. But again, here gives you the LEDs, 60-watt lamp, and then how it drops down and long working hours. So this is what these kind of nanostructures are being used. You can tune the band gap of based on the different semiconductors. And again, you can take a look at some of these reviews. But the bottom line is they're simple, easy to make, and also you can tune whatever wavelength you want. So these are already in the LEDs, people are using it. Another application is in what they call is an up conversion. That means you can take a low energy photon and then you can make it a high energy photon, because most of the time the low energy photons are wasted anyway. So even if you take 2 photons and make it into 1 high energy photon, you can utilize that. And that is another area where these semiconductor nanostructures can play a role. Okay. So we talked about most of the things in energy sector, right? All the morning talks you heard and even more. That's only 40% of the carbon footprint, the energy. The 60% of the carbon footprint comes from other sources, mostly manufacturing, steel, cement, okay, fertilizers, all these things, right? We cannot just take care of 40% if we are going for net zero. We need to find out other things. So that's what I will focus the next part on beyond photovoltaics and what are the opportunities. One is solar fuels, right? So the water splitting, making hydrogen, again, the photocatalysis, electrocatalysis, I will talk about a little later. And this is where Europe is mainly focusing on hydrogen. In the US, the focus is on reducing carbon dioxide. That's what the 2 hubs of the DOE, one in Caltech and one in UNC, they're focused on CO2 reduction, so much on CO2 reduction. Somehow, again, there may be small supports for hydrogen generation, but the most focus of DOE seems to be on this one. To me, if you make a fuel and burning again, you're making carbon again, right? So that's, again, it's a more different topic for another day for discussion. So photocatalysis with nanoparticles. You can use the same nanoparticles I talked about. You can do these reactions. Advantage is that now you have got large surface area to do these reactions. You can tune the structure by just composition or size, shape, those kind of things. But they're inherently inefficient because of competing charge carriers. So you excite these ones, you generate electrons and holes, they try to recombine back. There is a strong tendency to combine back. despite 5 decades of research, no practical solution yet to implement photocatalysis, any processes. It has remained in lab. To deionize water, it works great. One of these ways to overcome is you need a co-catalyst to drive these electron holes in the opposite direction and make it happen. So that has been a strategy. Otherwise, you have to take away like sacrificial donors and then promote it. This one works great, but you are also consuming other chemicals. Again, there are various materials, semiconductor materials people have tested. Their band energies and band gaps are different, and you can tune it to drive different reactions. So these are like from carbon dioxide reduction to oxygen generation. Again, these perovskite nanocrystals have been used for hydrogen generation, some of the organic transformations, and also polymerization reactions. We have been working with bipolar membrane. So this is going to be a big thing coming years is the membrane technology. Okay, so whether it's not only water purification, but as a separator for various things. So we use this one in the cation exchange and anion exchange membranes. We can make selectively in the membrane cadmium sulfide and then deposit gold or platinum or whatever it is. And just to show you, you can just in a thin membrane, you can make these ones and insert between the two cells and shine light, and you can generate hydrogen. And in this case, we were testing some of the sacrificial donors, how much hydrogen they produce. And sure enough, you can get the hydrogen generated, okay? So again, this is a photocatalysis principle to show how a hydrogen is working. So now the photocatalysis versus electrocatalysis. Why electrocatalysis wins, right? So this is where you use a semiconductor electrode where you generate electricity, same electrode when you put in water or things. So the electron are driven, come to the counter electrode, and you have a separator here. You can do the reduction reaction and you can do the oxidation reaction. In fact, there is a lot of electrochemical synthesis of chemicals are being tested. That is one of the things. This is, a photoelectrochemical synthesis. This in the electrocatalysis, simple, you need a power source. Now, because of the plenty of renewable energy, they are using this power, and now you can drive the same reactions at the electrode surface, okay? The two of the biggest chemicals that are produced is aluminum and sodium hydroxide, pure electrochemistry. So if someone says electrochemistry cannot be used in synthesis, give these two examples. So electrochemistry can work in synthesis. This is the example for photosynthetic PEC cells published by Domain. He put the strontium titanate solar cell in the field to show that they can get 100 meter square scale, they can get it. But again, the plus and pros and cons of these processes. What is happening right now is the focus on water splitting to make hydrogen, okay? So affordable green hydrogen from alkaline water electrolysis, there is a perspective, and there are three main technologies. One is alkaline water electrolysis, proton exchange membrane water electrolysis, and solid oxide electrolysis. When you try to make it a large scale, you cannot use, I can use platinum electrode in my lab, but in an electrolyzer, you have to have a more common electrode. And they are using nickel oxyhydroxide, NiOH, and that works only in alkaline electrolysis. So that's where it is coming. And then there's also solid oxide electrolysis. I'll just give you, this is Siemens. They are making a 8.5 megawatt PM electrolyzer. You can buy it tomorrow. Okay, Siemens Energy is selling, and the green hydrogen is a versatile energy carrier that can be applied. And you can see here the plumbing to drive this hydrogen and oxygen and those things. That's why I'm saying that Europe is more focused towards hydrogen generation. But once you generate it, you can decarbonize. So it says only around 40% of global carbon dioxide emission originate from power generation, which can be decarbonized via electrification. But you need other sources to make it. Here is a science article in solid oxide cell technology. Again, they are using this wind and solar, they drive these ones, they can use it to make chemicals, fuels. Again, this is a cartoon, but the way they want to use it, directly feeding to the industries to make chemicals, right? Steel today we dump in coal to reduce it. It burns it, at the same time gives you reduced iron oxide to iron. Why not use other reductants that are clean? Hydrogen is a reductant. Okay, that is one of the things that's going in. Then there is a solid oxide cell technology that you can see here. Again, these are stacked cells. They bring in the gas phase, the steam and other things to make it. Again, you can make methanol, you can make other ammonia, and then the fertilizers, right? So again, that is one of the things why hydrogen is becoming. And here it is, Denmark is putting $1.25 billion for hydrogen production because they have so much excess wind energy. They don't know what to do with it. They have to stop the windmills, right? Or give it free to somebody. Even in California, they say, we have excess wind energy. They give it free to Nevada. So that one, you can use it. Here is a one from Japan. There is a solar panel here, and this is the electrolyzer. So this is what it is happening other places. This came out 2 days back in Wired magazine. Forget cars, green hydrogen will supercharge crops. And they are going to say that this company has now joined to make hydrogen to make basically ammonia for fertilizers. The production of ammonia for fertilizer contributes about 0.8%. It's a small amount, but still significant. So it's a magical hydrogen which is produced through natural significance. And I was just glancing through yesterday, CNN News said, this is yesterday, under pressure, Johnson Matthey seeks profit in hydrogen because their profits are going down. Now they see hydrogen production is a possibility. So again, where we are right now. Okay, if you talk to a lot of people, they say, no, hydrogen cannot be stored, hydrogen cannot be transported, but same people told you about photovoltaics 10 years back, that it is not feasible. That's what I say. If you look at what happened with solar, both solar and battery systems came down about 80% in 10 years, the cost. The same will happen with hydrogen once it finds more solid technical ground. Again, this is from that article, okay, it's not my word. Okay, here is the net zero, right? I will not live to see the net zero in 2050. That's guaranteed, okay? But these are for others, my next generation or the future generations. This is, if you go to the BP or Exxon, every year they have an energy outlook. They forecast, and it changes every year. But this is what their fossil fuels will decrease under 3 scenarios. One is accelerated, the blue one is net zero, and with new momentum. So you can see here, if you say net zero, we are 80% right now, we have to drop to 20%. And again, electricity demand will go up, and that will be filled in by renewable. But look at this low carbon hydrogen. The BP is predicting, right now we are here, almost nothing. By 2050, they are predicting significantly higher production. So this is to me, plays a critical role in decarbonizing the energy system, especially in hard to abate processes and activities industry. So it is not only electrification, we need to take the other sectors too. Okay, to summarize, again, this was shown earlier, slide 2. So this is what we need for 1.5 degrees to get into where we are. And these are the current projections where we will be. You can figure it out. Until now, reduction of CO, carbon dioxide is mainly focused on renewable energy, through renewable energy. But efficiency improvements and other things. But we need to not only decrease the carbon footprint of making of these materials, but also we need to focus on other sectors, how we can do it. There are a lot of low-hanging fruits. We can do it, and fossil fuel usage will continue to contribute. about 20% energy mix and need to develop strategies for large scale sequestration. So we will hear, if you see it here, this will still be fossil fuels. This will be done by sequestration, CO2. And finally, this is one of my favorite slide by Harvard, New York University. In 2002, he published a Nature article. Harry said that we need to create a global grid. And people say, wait a minute, how can you create a global grid? We did create a communication grid. Why can't energy grid, right? We can, if it is cloudy here, sunny somewhere else. If it is not wind here, wind is there somewhere else. So we can all integrate different energies and we can solve the problem. But we need to be working together on this one. And this way, another one. So again, this is a great idea. So he's all this figured it out. Okay, finally, my last thing. This is, if you haven't read what this George Carlin thing, he says the planet is fine compared to the people. The planet will be here, will be long gone. It's not for planet. It's like, it will survive. It's for us, our future generations. Thank you.
Thank you very much. We'll take one question. Yes, in the back.
Thank you for your presentation. I did notice that some of the photovoltaics you mentioned contain lead. And has there been any kind of life cycle analysis to understand the environmental and health implication? So you talk about putting lead on top of solar panels, then if there is any kind of flaking that happens, it's going to be in the air. So is there been any life cycle analysis to determine what that would look like?
One of them, there have been some analysis have been done and people are doing it. Number one, almost everyone who drives a car carries 50 pounds of lead in their cars. Okay, every car has a lead acid battery. Number two, First Solar makes cadmium telluride based solar cells. They are the only ones who recycle the solar cells. And the 10% of the solar market is, and cadmium is a battery. But they have recycling plant. They even sell it in Europe. They have plant in Europe. For lead, the amount is so small. It is the emitted lead, I can send you a paper, the calculations, is less than what coal-fired power plants emit in the atmosphere. If you replace all solar cells, it's perovskite solar cell, and assume that everything goes into the atmosphere, that lead is still less than what power plants emit. So I'm not saying that the first example of First Solar tells you that we can manage. Same way with the lead acid batteries. We know how to contain and recycle. So those aspects need to be put in.
No, I do agree with you, but I think there might be, it might be important to quantify that, because when we do life cycle and when people do life cycle analysis, I don't do it. It's not only about how much we are putting out in application, but we also need to think about the footprint of mining the lead, which
you don't need to mine the lead. There is enough lead around, believe me. What happens to the lead acid batteries?
So you recycle the lead acid batteries and use.
Yeah,
but again,
we have enough lead. Believe me, you don't need to mine lead. Right. And it needs, I showed you how minuscule it needs for generating. Yeah, but I agree with you, it's an environmental concern. But people who make technology, I gave an example of First Solar. It is just, they have to follow First Solar. And recycling, we have to follow the battery part.
Thank you.
But there are papers out there, which I don't have right now, but I can send you.
Thank you so much. And for time, I'm going to have to say no more questions. The presentations this morning have been so fascinating that I've been doing a horrible job of keeping people on time. But we are going to move to our next speaker. Thank you so much. And this is the last presentation of the morning. And then I think we have a lunch and a luncheon speaker. The third speaker is Dr. Gareth Neville Hall from Lawrence Livermore National Laboratory. And the title of his speech is, or talk is Reaching Fusion Ignition on the National Ignition Facility. And so without further ado, I'll turn it over to Dr. Gareth Hall.
Okay, good morning, ladies and gentlemen. First of all, thank you so much to the organising committee for inviting me here today. It's an absolute honour. I'm here today to talk about reaching fusion ignition on the NIF. I'm a research scientist from NIF. I'm from the NIF X-ray Measurement and Diagnostic Science Group, and I'm here representing a lot of people. I'm here representing the inertial confinement fusion community at Livermore and from all over the world. So, a few months ago, you might have seen this headline in the news. On December 5th, 2022, the National Ignition Facility, the NIF, achieved fusion ignition in the laboratory for the first time. About 3 megajoules of fusion energy was produced using about 2 megajoules of laser energy for a gain of 1.5. Now, that is a complicated headline. If you aren't an expert in the field, some of those things might be completely opaque to you. So today I'm going to go through and talk about what exactly this means. What is fusion? What's ignition? Why is it important? What is the National Ignition Facility and how is it used for fusion research? And what are the challenges for making a fusion power station? So let's start right at the beginning with what is fusion? Well, fusion is the process that powers the sun and the stars. Stars take hydrogen, they fuse it together, and out comes helium. Now, on NIF, we use deuterium and tritium, which are isotopes of hydrogen, and they are the easiest isotopes to fuse. So the ingredients for our fusion reaction is 1 deuterium atom and 1 tritium atom. And we fuse them together, and out comes helium, neutrons, and some energy. Well, actually, an absolute ton of energy. For the same mass of fuel, fusion produces 4 million times more energy than burning oil or coal. It's an incredibly energy-rich reaction. So if it is that rich, can we harness it? Well, we can, but it's very difficult, and here's why. Look at the ingredients. They both have a positive charge because these nuclei have a proton in them. And to try and force 2 positive charges together is difficult. They want to repel. So how do we make them get so close that they fuse? We have to get them really close. We have to smash them together really hard. Now, in the atomic world, making things go fast and smashing them hard means very high temperatures. So we need to get to high temperature and high pressure, kind of like what happens in the core of a star. So we need to make a miniature star on Earth. And how do we do that? Well, I'm here to talk about a technique called inertial confinement fusion, ICF. Now, this can be achieved by using high-power lasers to drive a spherical implosion. So what we do is we use the laser to produce X-rays, and the X-rays rapidly heat the surface of a capsule which contains our fuel, our deuterium-tritium fuel. So here's the capsule. The X-rays cause the outer surface of the capsule to blow outwards. Well, from your high school physics, you should know for every reaction, there is an equal and opposite reaction. So as the outside blows out, we implode the fuel, it goes inwards. So this little fuel capsule gets imploded by the X-ray drive. The fuel stagnates, it crushes in on itself, and it creates a hot central core surrounded by a dense confining shell. And if we do it right, the core should ignite and the fusion burn propagates into the dense fuel shell, and you should get more energy out than you put in. That's the plan. Anyway, and what does ignition mean? Well, ignition just means that the fusion output must be equal or more to the laser energy input. It just means we should get, ignition means we get out more than we put in. Okay. Now notice I said that we don't drive the capsule with the laser directly. We use the laser to generate X-rays. So how do we do that? Well, the NIF uses what's called a Hohlraum. Hohlraum is from the German word meaning cavity. And what it is a cavity. So here's what the Hohlraum on NIF looks like. It's a little cylinder. And inside that cylinder, we have the capsule, and we put in many, many laser beams through the ends of this cylinder so that they hit the walls. So the Hohlraum walls convert laser energy into X-rays, and then it's the X-rays which compress the fuel capsule to fusion conditions. So here's kind of a simulation of what that looks like when you do it. Here you're seeing laser beams coming in the laser entrance hole. They are hitting the wall of our depleted uranium Hohlraum, and they're heating it, and it's getting hot, and it's giving off X-rays. Those X-rays are causing the exterior of this capsule to explode outwards and implode. So the X-rays blow off the capsule wall. It accelerates that fuel inwards at 1,000,000 miles an hour. It's incredibly fast. And the DT fuel is compressed to 100 times the density of lead and gets 10 times hotter than the core of our sun. Now, just to give you an idea of how much we squeeze this thing, if the capsule started off at the size of a baseball, the size of a basketball, we're reducing it to the size of a pea. So it is an incredibly high compression. Okay, so we need a very large laser to do this. In fact, we need lots of very large lasers. So we use the National Ignition Facility. It's the world's most energetic laser, and it enables the creation and study of extreme conditions. Here's a picture of the building. We actually have 192 of the world's most energetic lasers for a total of 2 megajoules of energy. We can produce 500 terawatts of laser power. That's equivalent to 100 million billion of these laser pointers, a rather powerful laser. We produce temperatures 10 times hotter than the core of the sun, densities 100 times that of lead, and we get to pressures that are 100 million times that at the bottom of the Earth's deepest oceans. So we create very, very extreme conditions like what happen in stars and elsewhere in the universe. The National Ignition Facility is the world's largest laser. It's a very big building. So here's the building from the air. You can kind of get a feeling of how big it is from the vehicles here. But here's a better analogy. It's the size of 3 American football fields. Pretty big. And it's 10 stories high. Let's take a look inside of it. This is kind of what it looks like when you take the roof off. These long kind of linear sections on each side here, these are the lasers. These are our 192 lasers. And eventually they will make a laser pulse that puts its energy into this section. And right in the middle there is a target chamber. And in the middle of that target chamber is our Hohlraum. You see how small it is? This is the guy holding it. You see the fingers? It's very small. And we take all the laser pulses from all this massive laser and we squeeze it into that little hole. And inside of that Hohlraum is your ICF capsule. This is the fuel capsule. You can see how small it is. It's about the size of a BB pellet. So we put all the lasers from that massive building to compress something the size of a BB pellet. Okay, so let's take a look at what it happens kind of when we go through and experiment. So here's the NIF laser from the outside. We're going to go inside now and take a look at the control room. In the control room before a shot, it's a little bit like a NASA control room, a little bit smaller than that maybe. We have scientists, technicians, engineers all getting ready, setting things up and making stuff good to go. And the first thing we do is we have to energize the laser. So first of all, we take electrical energy that's been stored in capacitor banks and we dump it into the laser. And that's energy that later on will get pulled out by the laser as it passes through to amplify it. Now, the laser doesn't start out as a large energy pulse. It starts out as a very low energy pulse because we need to make it very, very precise. So we use these banks of small lasers here, And each one of them produces a little pulse, and we stitch them together to form a pulse in time that is incredibly accurate, just what we want. And once we've got what we want in this low energy form, we send it out into the main laser bank. So off it goes out to the sides, and that's where we dump the energy earlier. And the pulse starts bouncing around. And as it bounces back and forth, it's sucking out the energy that we put in to start with. It's being amplified again and again. Let's get this. Get rid of that. Can someone get rid of that for me? I can't actually get to clicking on it. Maybe someone else will have to get on that. Anyway, so as the laser passes through these bits here, which are kind of glowing white, it's pulling energy out of the laser and being amplified. The laser pulse is not continuous. It's a short pulse. Don't come out of the... Oh. Okay, hold on. I don't know if this is on my computer.
You have to come out of the presentation
I'll
mode
come out of
first,
the
and then
presentation.
you can do that.
Okay, hold on, let's do it. Let's stop sharing. I don't think that's on my computer. It's not on my computer. Oh yeah, thank you very much. Thank you, great. Thank you very much. Okay, let's continue. Okay, I'm good to go. Thank you so much. Yeah, fine. Sorry, we have to watch a little bit over again because I can't start otherwise. Thank you so much. Sorry about that. I can't fast forward it, unfortunately, so you'll just have to be patient and see the movie again up to that point. Okay. Go, energize the laser. Build a small pulse. Okay, so here we were. So yes, it's bouncing backwards and forwards, and it's gathering up and sucking out the energy that we dumped in there earlier. And let's see, so as it passes through the amplifiers, yes, it's pulling out the energy. Here is what the pulse looks like. The laser is not a continuous pulse in time. It's a very short pulse. It's 10 billionths of a second long. That's a pulse of light that's about 10 feet long, actually. And it's going to make one more pulse. It's going to make one more pass through that amplifier, and then it's going to continue on towards the target chamber area. Okay, so here are some more beams joining it. Now you'll see there at that point, the laser beams are all in a parallel line. But if you remember the diagram earlier, we have to kind of inject them into the ends of this cylinder. So we need to rearrange them. So we rearrange these beams using mirrors and tubes. And now, as they approach the target chamber, which you can kind of see in the background there, they are now in a conical formation heading towards the target chamber. So here is the target chamber. It's 30 feet wide. Our target's right in the middle of it. Everything I've showed you so far, the laser is in infrared. But for our experiment, we need the laser to actually be in ultraviolet. So the last thing we do before we inject it is convert from infrared to green to ultraviolet. And so that then goes through some very large lenses, which focus the beams down so that now they are very small, a very small beam spot, and we can squeeze them in to the ends of the Holman. And here they are. They're all going through the laser entrance holes. They're hitting the walls are getting hot, they're radiating X-rays, and the capsule is imploding. Off it goes. Now, the laser pulse is 10 nanoseconds long, but we get all of our fusion energy out in a pulse of neutrons that only lasts for 100 trillionths of a second, 100 picoseconds. So it's very, very short. And then we take pictures of what's going on. They get back to scientists like me who can look at what's happened and go, okay, it went well, it went badly, and we can figure out what to do next. And this all happens in this building, which is in Lawrence Livermore. No, it's okay. I've got it this time. I've got it. There we go. And this is up in Northern California. So those experiments require some of the most precisely engineered targets that can be made by our target fabrication team. Here's a picture of one. You might recognize it from the movie you just saw, where we have the holograph here and we have the entrance holes here and here. The engineering that goes into these things is quite fabulously precise. Now, I actually brought one with me, so I'm going to pass this around. Take a look at it. Make sure it gets back to me at the end. If you don't get a chance to look at it, I'm here all day. You can come and find me. Don't worry, there's nothing in here which can hurt you. Pass that around. That is an ignition holder. The hologram, it's about 1/2 inch long, 10 millimeters, and the capsule is supported in the middle there. It's sandwiched in between two very thin pieces of plastic, which we call the tent. And that diamond, that capsule is actually made of diamond. It's a diamond shell, and here's what it looks like. It's a kind of it's very highly polished. So it's 2 millimeters diameter, but the surface is smooth to 10 nanometers. That's incredibly smooth. What that means is that if you blew this capsule up to the size of the Earth, it would mean the difference between the highest and the lowest points would be 190 feet. That's all. It's incredibly smooth. And it contains a layer of frozen hydrogen fuel at cryogenic temperatures. So if we take an X-ray through the capsule, a bit like when you go to the hospital and you take an X-ray of your bone, this is what a cross-section of the capsule looks like. That outer band and the black band as well, they're both the diamond. But if you look closely, you'll see this other layer on the inside there. You see that? That is a layer of deuterium tritium ice. And that layer is about as thick as a piece of your hair, about 50 microns. You have to make things pretty cold to make hydrogen freeze. So these capsules are cooled down to about 19 Kelvin, minus 425 Fahrenheit before the experiment. So we make stuff really cold to get it ready before we make it really hot. And you might be wondering, well, how on earth do you put the fuel inside a diamond shell? Well, we have a tiny little fill tube. So right down there at the bottom, you can see this little hair feature. That is a glass tube. It's a tube, and it's 2 microns in diameter. That's 25 times thinner than your hair. And we drill that through the wall of the diamond, and we use that then to fill the capsule with fuel before the experiment. So what I've told you there, now maybe this headline makes a bit more sense, I hope. Here it is again. NIF delivered 2 megajoules of laser energy and produced 3 megajoules of fusion energy. So that was a gain of 1.5. So I mean, we got 1.5 times out the energy we put in. This shot was accumulation of over a decade of experiments and learning on the NIF. Here is a plot of the year versus the fusion yield in megajoules. And this pink line here shows the laser energy which we had available. We started experiments in 2011, but I should say before 2011, there was 50 years of fusion research which went on beyond that. And you can see that our fusion yields to start with were really small, way below the laser energy. And we learned and we learned and we learned. And then in the late teens and early 20s, things really began to push up until finally here, 2022, finally our yield went above the laser energy. So this, with 50 years of fusion research before that, this accomplishment took 60 years to get right. That's how hard this is. Achieving ignition required a concerted long-term effort to improve the target quality, the laser accuracy, the laser energy, diagnostic capability, so we can see what's going on. The design of the capsule, the design of the hologram, the design of the laser pulse, these are all things which have changed enormously over the last 10 years, let alone 50. So This ignition result provides kind of a fresh impetus and the scientific foundation for something we call inertial fusion energy. That's the idea that maybe we can harness this energy in a power station. Well, what would a power station look like? So an inertial fusion energy, what we call it, inertial fusion energy, power plant would require igniting a high gain capsule more than 10 times a second. So this is kind of a concept, and it'll sound like science fiction right now, because right now it is science fiction. But the idea is that you have your laser driver that can be injected through the wall of your chamber. You've got to inject targets from the top, bang, 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 again, and then the laser will track them as they fall down and shoot them. When they ignite and give out their energy, remember the energy comes out in the form of neutrons. So the neutrons fly outwards and we catch them with a lithium blanket. So there is a lithium blanket on the inside of the chamber, and lithium is very good at catching neutrons. And when it does, it gets hot. We're putting energy into it, it gets hot. So we do a heat transfer out, it goes through a heat exchanger, and then we drive a turbine. So although this is cutting edge fusion research, we think we just got to make steam to turn the turbine. We don't have anything else at the moment. So that's the idea. Now remember, the ingredients for this reaction are tritium and deuterium. Now deuterium is a stable isotope of hydrogen. About 1 in every 6,000 hydrogens in the ocean is a deuterium atom. So we can just take our deuterium from seawater. Tritium, however, is an unstable isotope. And because of that, it decays. And so in nature, there's not a lot of it around. We have to make it. Well, here's the lucky thing about lithium. When you hit lithium with a high energy neutron, it splits, and it splits into helium and tritium. So by using a lithium blanket, we not only use that to capture the neutrons and capture the energy, we use it to breed a tritium fuel. So this is called a breeder blanket. So out of this comes tritium, and we can take that back into our targets, put it in with the deuterium, and we go again and again. So this, so we think we need about 900 cycles per minute, 15 a second, at a gain of 100 would provide a 1 gigawatt electricity power station, taking into account all the other inefficiencies in the system. Now that sounds like a lot of stuff going in, right? That sounds like a huge amount of things. Well, because of the energy density of fusion reactions, a reactor producing 1 gigawatt of electricity would require 5 tons of fuel a year. That's all. Compare that to a coal power plant, which requires more than 3 million tons of fuel a year, and you begin to see why people are very interested in the idea of fusion energy. But it is difficult. The leap from NIF to an IFE power plant is going to require a massive increase in repetition rate, a robust and repeatable high gain platforms, many technological advances. So NIF is a single shot, and IFE plant, we've got to do that at greater than 10 hertz. The challenges are many. First of all, we've done ignition, but now we've got to get high gain, not 1.5 times the energy out. We've got to get 100 times the energy out. We've got to, so NIF is old laser technology now, and it's inefficient. We've got to make a high efficiency, high rep rate laser. The targets that went into this ignition shot cost hundreds of thousands of dollars. Don't worry, the one you're handling does not cost hundreds of thousands of dollars. We've got to be able to build 15 targets a second at very low cost to make this economical. And also, we've got to worry about the lifetime of the chamber and the optics. When neutrons hit things, it damages materials. So we have to be careful, understand how long will things survive. We need neutron resilient materials. So the challenges are many, but the benefits are huge. So scientists have always said, and you know, fusion really is the holy grail of energy production. Well, it is, and it may be the ultimate clean and limitless energy source. And here are some reasons why. It's very safe. Now, when people think of nuclear power, you're typically thinking of fission, right? Splitting heavy atoms like uranium. Personally, now I understand, and we all should understand, that nuclear fission is a very safe, good alternative, but it does have its risks. Fusion has none of those risks. I won't have time to talk to you about it now. You can ask me a question or talk to me later if you like. It's carbon free. The the stuff that comes out of this reaction is helium. There's no carbon dioxide involved. It's sustainable. Like I say, 1 in every 6,000 hydrogens in the Earth's ocean is deuterium, and we make our own tritium. It's great for energy security, sovereignty, and diversification. That's things which we should be concerned about. A power plant would be a baseload power plant, as in it could be always on. It's not an intermittent. It doesn't need good weather conditions or particular geological location. So it has some of those advantages over other forms. And there's no geological storage because we're not producing carbon dioxide. So the benefits are enormous, which is why people are so interested in it. So in summary, I'll just say a few things before I finish. The recent game-changing NIF results lay the groundwork to kind of explore inertial fusion energy as a path for clean energy. Inertial fusion energy is difficult. It's going to be the next scientific and engineering grand challenge. Making IFE a reality will take decades. It takes a long time, and it will require new technologies that don't even exist right now. The scale of investment needs is comparable or probably more than all prior fusion research. So not just research on NIF, the last 60 years, we'll probably need as much, if not more funding again. And however, fusion energy really does offer a very long-term vision for climate and energy security, because this stuff could just be around forever. Once you've harnessed fusion energy, you're done. So with that, I will say thank you very much for your attention.
Question in the back?
The game result is exciting, but I imagine it took a lot more wall power than those 2 megajoules to produce the 2 megajoules of laser power. Do you have a sense for what that number is?
Yes, absolutely. That's a great question. So NIF is old laser technology. The reason we put the result in terms of the laser that went in versus the wall plug is because there are new lasers around now which are a lot more efficient. And so really it was kind of in terms of if you had any laser, what would you be able to do? So NIF, we actually put about 300 megajoules from the wall plug because the efficiency of that technology, which is from the 80s and 90s, 1980s and 1990s, it's about 1% efficient. So very low. But because it's pumped by flash lamps, which are like an old light bulb, they're the old tungsten filament light bulbs or like fluorescent bulbs, they're very inefficient. Whereas now we have LED powered lasers, which are like 20, 30% efficient or even more. I'm not sure what the very latest result is, but yeah, it's an old laser. A new laser would, you would absolutely have to have a more efficient new laser to make this worthwhile. But if you had that new laser and you put 2 megajoules of it in, we've still got the 3 out, which is the important part, I guess.
Rue, first.
This is incredible. It's almost like Star Wars. But my question is, I understand there are 2 startup companies.
There's a lot of startup companies.
How will they be able to do what you have accomplished after 60 years of, and how did you startup companies will do this?
To give you a trite answer, I'd say stand on the shoulders of giants. Because remember, this research is out there. It's there for you all to read. This is not something that's hidden away. We could tell you all how to do this, and we are partnering. So these companies are going to have to partner with us. The Lawrence Livermore and the DOE are actually working in close partnership with the broader community to support that emerging landscape. So we actually are currently inviting fusion startup companies to the lab to talk to us so that we can teach them how to do it and give them support, because this is going to take a partnership between government alone can't do this, and companies alone can't do this. It's going to take a massive collaboration between world government and the private sector, an enormous collaboration, and it will cost a lot of money and it will take time. So yeah, it's going to be hard. There are some companies out there with very, very optimistic timelines. You've got to be careful about that. But we're working with them.
One more question, Prasad.
Short question. You said that it's sustained for a couple of picoseconds. How to make it more sustainable?
Well, actually, when you make it better, it gets shorter. So remember, this power plant is like your car engine. It's like bang, 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 bang. Your car engine is not, you wouldn't say if I made my pulses in my combustion engine longer, my engine would get better. The idea is each pulse needs to give out more energy. So at the moment, with that ignition result, we actually only burn up about 3% of the fuel that we put in there. I'll talk to you outside why we're limited by that, but in future, we would like to burn up a lot more. Now, the thing is, as you burn it, it gets hotter and it fuses quicker. So actually, the better you do, the quicker the energy comes out. The point is, we're going to average that over 15 cycles a second. You would, just like when you put your foot on the accelerator of your car, you get more.
Is the ultimate goal is to make it self-sustainable, or it is just always you have to put in some energy to keep it?
Oh yeah, no, this is a pulsed form.
This is a pulse, but in the long run, if you want to go on a manufacturing scale of energy, will it still require constant input of energy?
Yeah.
Or it will be self-sustained?
No, well, okay, it's self-sustaining once you put the energy in. But remember, it's only self-sustained for one pulse. So yes, so when I say these numbers are based upon, the gain of 100 means that you still got to put in your 1 unit of laser energy to get 100 out. So it's going to be pulse. There are ways of doing this. I'm sure you've heard of magnetically confined fusion, things with tokamaks. These are continuous drivers. So yes, they have a continuous burn. We are a pulse burn. So tokamaks are kind of like the pressure cooker way of doing it. It's sort of a very large volume of plasma, which is burning quite slowly, but it's on all the time. We're kind of like the combustion engine way of doing it, where we're going pulse, 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 pulse. So, and they each have their pros and cons. I don't know which one is going to get there first in terms of putting power on the grid. But it's important that we look into lots of options so that we're not limited to one technology.
One more question. Yours is the last question.
And you can answer it if it's too long for lunch. But if you look at the others, like we keep reading about the ones in the UK, in China, and then ITER, what are the principles behind them and where are they related?
So that's kind of almost the answer I just gave. So the one that you're hearing about in France, the ITER, that is called magnetic confinement. So they hold a very large volume of fuel with a magnetic field in a big magnetic bottle called a tokamak, right? And so that is kind of the pressure cooker approach. It's very low density fuel actually, but they have a large volume of it and it's kind of cooking slowly and then neutrons are coming out continuously. We are the opposite approach where we get it done fast and fast. But overall, the power out at the other end is the same. So when you hear in the news about ITER or the Oxford Jet tokamak, I presume is what you're talking about, that's the slow and steady with the pulsed version. As I say, they have pros and cons. Each of them have advantages and disadvantages.
Thank you so much. That ends our session. We are breaking for lunch. Lunch is served outside in the Collaboration Hub. We're requesting that everybody be back in here by 1:15 for our luncheon speech by Josh Shiloh, the Chief of Staff of the Office of Energy. So lunch is outside. Thank you.
Well, good afternoon. We probably should get started so we can keep on time. It's a great pleasure for me to introduce Joseph Seodale. He's the Chief of Staff in the Office of Science. He received his PhD in astrophysics from UC Berkeley and BA in astronomy from Boston University. Prior to joining the Office of Science, Josh was Federal Affairs Director for the Pacific Northwest National Laboratory, bringing the lab's capabilities and expertise to bear on critical national issues. He also served as Director of Government Affairs for the Semiconductor Industry Association, Senior Government Relations Officer at the American Association of Advancement of Science, and the John N. Beckel Public Policy Fellow of the American Astronomical Society. It's a pleasure to
Yes.
meet you.
Thanks. Thank you very much for the introduction. Today I'm going to tell you a little bit about the ways the Department of Energy, in particular the Office of Science, where I'm coming to you from, is working across the government to address the climate crisis, as well as invest in basic science across all sorts of fields, including a lot of stuff going on here at VCU. So you heard from Costa this morning, I understand, a great talk about sort of the whole of government approach. So I'm just going to focus in on what our secretary likes to call the solutions department. And our national labs, our solutions factories in the Department of Energy. And in particular, the Office of Science. I'm here on behalf of the director, Dr. Aspirin Estefan-Berhe, who unfortunately wasn't able to be here today, and so sent me in her place, and I'll do my best to fill her shoes, although my shoes are actually a little bigger. Across the board, we are taking bold leaps and action against the climate crisis. And I would say this is a great example, which your previous speaker will recognize, a picture from the NIF event. This is not an Office of Science investment, but an example of one of the many things the Department of Energy across the board is doing to advance clean energy solutions and address climate change. We're taking a bold view of this problem and trying to lean on our history of bold leaps. You know, on your left, you see a picture of the early Manhattan Project. This is the foundations of the Department of Energy are really making these bold leaps into the future to try to address a major national crisis. So we're taking a moonshot approach to this. And right at the beginning of the Biden administration, the Department of Energy launched what are called the Energy Earthshots Initiative. And right now there are 6 Energy Earthshots that we have launched. And these are meant to be bold, achievable goals with clear metrics that align the programs of the Department of Energy around these key priorities. So what are these actually? Let me give you a couple of quick examples. So for the hydrogen shot, hopefully you've heard of this. This is the one that's been around the longest. It was the first one that the department launched. And I'm looking a lot at Seth here because he knows all this stuff working at Argonne and is working on a number of these. But the hydrogen shot goal is to get to $1 to produce 1 kilogram of hydrogen within 1 decade. That is the goal that is being set. And there are many challenges that we have to overcome. When we look at this from the Office of Science perspective, we are the basic science part of the department. We're thinking about things like material science, chemistry, surface characterizations, different types of materials that we will need to make this possible, the membranes, the chemistry that we need to advance. So we're going to make investments at that foundational level, while the hydrogen and fuel cell technology office is going to invest more on the applied side. And we have the hydrogen hubs, which are being considered, proposals are being considered right now, that are going to try to bring together industry, universities, national labs, and everybody to the table to move this forward, as well as starting to address some of the infrastructure challenges that exist around these key technology challenges that we have for our climate change future. The next one I would highlight is the energy storage challenge, where the goal here is to reduce the energy storage cost by 90% from the baseline of a 2020 lithium ion battery technology in a full-scale storage system that delivers more than 10 hours of duration. So that's a big part of this challenge, is that duration piece. You know, for those, I think many are familiar with lithium ion and other battery technologies. Most of these things on the grid are 4-hour duration. So this is a huge challenge. Can we do this in a lithium system? Do we need other types of systems? All technologies are on the table for this challenge, this long duration energy storage challenge. It doesn't have to be batteries. It certainly doesn't need to be a lithium ion chemistry. It can be all sorts of things like flow batteries, mechanical systems, deep boreholes, all sorts of things that are out there. This shot will galvanize the community of the Department of Energy's programs around advancing these technologies that can really reach this goal on that decadal timescale. And so from the Office of Science, again, we're thinking about things like, again, chemistries, but also subsurface science, also modeling and materials that need to see new scientific discoveries in order to unlock future technology advances. And then the last one I'll mention is get the carbon negative shot. So coming up with technologies that for less than $100 can store 1 ton of carbon dioxide, again, within 1 decade. And we want to be able to store this at gigaton scales that are relevant to the actual challenge we face and sort of concentrations of CO2 in our atmosphere. This is critical worldwide to put the US in the lead of this emerging industry that is going to need to exist around the world if we're going to address the climate challenge in front of us. Again, there's huge challenges in chemistry and subsurface science and other things that where the Office of Science and its basic research investments are going to play an important role. So thanks to Congress, we have brand new tools that didn't exist just a year or two ago to address these challenges. And here I'm talking way outside my swim lane, so I'll give you the best possible I can do because this is all outside the Office of Science. But for more, I'm happy to connect you with other colleagues who are more engaged in these programs. But on the bipartisan infrastructure law side, this was all funding that's really focused on unleashing deployment of these future clean energy technologies. This provided over $60 billion to DOE over 5 years for new programs like the hydrogen hubs that I mentioned. But also long duration energy storage demonstration projects on various federal sites or using former mine lands to produce energy in clean and renewable ways. So this is a really amazing set of capabilities, set of tools that the Congress has given to the Department of Energy that are just now being rolled out and unleashed. And this is going to be something you're going to see from the department over the course of the next several years. The other one I'll mention, which does have a connection to the Office of Science, is the Inflation Reduction Act. There are sort of three pillars of this law, but the biggest piece from the Department of Energy perspective is this is the biggest climate change investment we've ever made as a country. A lot of this has to do with tax incentives and other things that are outside the Department of Energy, but on our side, there's a lot of investment as well in our national laboratory infrastructure and in technology programs that will advance the clean energy goals that we have. For us in the Office of Science, the big exciting piece of this was $1.5 billion to invest in the national lab infrastructure across the country. So the Department of Energy's Office of Science runs 10 of the 17 national laboratories that the Department of Energy has. And this investment from Congress went to user facilities and other infrastructure challenges across this network of laboratories, as well as you'll see Michigan State University on there because they have the facility for rare isotope beams, a scientific user facility for producing rare isotopes, as the name suggests, in Michigan. So the third piece of legislation I would point you to is the CHIPS and Science Act. You've probably heard a lot about the CHIPS part of that bill, investing $52 billion into the semiconductor industry in a variety of mechanisms. None of that money all goes to the Department of Commerce, the Department of Defense, and the Department of State. But the Science Act piece of this is the first comprehensive authorization for the Department of Energy's Office of Science in its history, authorizing all of our programs and proposing to spend upwards of $50 billion over 5 years at the Department of Energy's Office of Science. Now, the CHIPS piece of that is what's called appropriations. It's actual real dollars people can spend out of bank accounts. The Science Act piece of that is what's called authorizations. It's aspirational targets that we're trying to hit. But I will say that the Department of Energy has just released its FY24 budget request. We believe this is a really strong down payment on that authorization. While we're not quite reaching the $9.5 billion proposed for the Office of Science in this bill, it would be a historic investment in science at $8.8 billion and really help us to move out on some of the key priorities laid out in this historic bill. The one piece that I would just highlight for you is we are right about meeting the authorized level for the Fusion Energy Sciences program. So you just heard about NIF, which is a part which comes to you through the National Nuclear Security Administration. But we also have a huge the bulk of the fusion effort at the department happens in the Office of Science through our Fusion Energy Sciences program. And so our FY24 budget will really strongly grow our investment in fusion energy sciences if the Congress were to grant us that request, which you all can make your own conclusions about. So that brings us to where I'm coming from today. So I'm coming to you from the Office of Science. As I've mentioned a couple of times, we are the basic science part of the Department of Energy. We live underneath the Undersecretary for Science and Innovation, sharing that space with the applied energy programs and technology transfer programs at the Department of Energy. We support nearly 30,000 researchers across 300 institutions and 17 labs every year. we steward 10 of the 17 labs. So they report into our office, and we're responsible for guiding the work and overseeing the work going on, including at Argonne. You'll hear from Seth later tonight. We have 28 scientific user facilities. These are really like the front door to the national lab system, I would say. And they support nearly 34,000 users across the country and across the world, including many are actually around the room here, folks at VCU. I did a little bit of pandering homework before I came and found several of you have used multiple of our user facilities, and I'll get into that a little bit later. And yeah, in FY23, you get tired of saying the word historic when it comes to the science budget because we have been at historic levels year after year after year. There's really strong support in this administration and in bipartisan way in Congress for the Office of Science. And so we've really seen incredible growth in our budgets that we're grateful for, and that I think is delivering a lot of great science across the country. We have a broad portfolio of, sorry, I lost my place in my little notes here. We have a broad portfolio of research across all these areas of science, but I would say there are three key pillars to our work. We are driving discovery science for the nation through the research programs that we run, fostering great minds and great ideas. This is a key priority for my boss, the director of the Office of Science, really making sure that the funding that we are providing to the community is really serving the public, and that means all of the public. And historically, that has not necessarily been the case. I'm going to talk about at the end, towards the end here, a number of programs we've launched to really broaden participation in our programs and better include organizations, institutions like yours that are MSIs around the country. And then providing these unique world-class facilities, the scientific user facilities we have. We have some of the most powerful light sources and computers that exist in the world. So this is a smattering of numbers. This is more of an eye chart than anything else, but I would just point to a few things. So as I mentioned, we have 6 core science programs across scientific computing research, basic energy sciences, biology, fusion, high energy physics, and nuclear physics. We also have some somewhat smaller programs in technology and engineering. So the Accelerator Research and Development Production program looks across accelerator technologies to see what we need to do in that space. Isotope research and development and production, we run large nuclear facilities that produce and accelerator facilities that produce isotopes that are important for everything from quantum information science to medical applications. And so that is a program in the Office of Science that we steward. We've got a number of different, I think the other thing that this chart communicates well is we have a number of different research modalities that we use in the Office of Science. So it's not just single investigator grants. We have large centers. The National Quantum Information Science Research Centers, those are $25 million a year, distributed centers across the country, led by national laboratories in most cases. The Energy Frontier Research Centers, largely led out of universities. These are incredible modalities that have existed for over a decade now, really driving team science. If there's one thing that ties a lot of this together, it's that the Department of Energy's Office of Science is really, really amazing at big team science. I would say that's true of the department overall, but really true of the Department of Energy's Office of Science. These are the 17 national laboratories across the country. We steward 10 of them, the ones in green here, in the Department of Energy, in the Office of Science. At those facilities, as well as at Michigan State, we have 28 scientific user facilities. So if you want to do something with the world's most powerful X-ray light source, or you want to use the first exascale computer recognized in the world, you can do that. And you can do that without having to pay for it if you have a great scientific idea and it gets through the peer review process. These are merit-reviewed processes to get onto these facilities. This is kind of just, again, a bit of an eye chart, but looks across the different things we have. So across the top, you see world's leading supercomputers, whether it's the highest performing ones like Frontier at Oak Ridge National Lab, the first exascale computer, or something like NERSC, which is a workforce computer for scientific computing that serves a huge swath of the scientific community for doing high performance computing, but not at that bleeding edge. ESNet supports scientific computing communications infrastructure across the country. We have a couple of facilities, EMSL and ARM, that are focused on environmental science. We have HIFER, which is a nuclear facility that does important neutron science as well as the spallation neutron source, but also produces isotopes. We have the X-ray light sources. We have nanoscale science centers where you can go use some of the most exquisite characterization and synthesis tools that exist. You can get access to these facilities. And I think the thing that I learned working for Pacific Northwest National Lab that wasn't apparent to me before was that it's not just the tools, it's the people too. So when you go to a user facility at the national labs, you may have an idea of how you want to use that pulsed X-ray light source, but you're going to get to work alongside people who do that every day as their job. We're going to help you tailor your experiment in such a way that you'll get the most out of that. And they can also often help you figure out how can you couple that with an investment in time at one of the computing facilities so that you can model the work that you're doing in a way that's effective. And so these are really incredible facilities, and I encourage you, if you haven't learned about them, I encourage you to learn about them. I have, I think, some links at the end, and connect with your colleagues who have worked with them as well. My director, Dr. Berhe, often talks about how this was her entry into the laboratory system. You know, she had an advisor who knew the labs, who got her access to one of the user facilities, and really opened the door to the amazing work that goes on across the complex. So this is our research portfolio I mentioned before. Advanced scientific computing research. We are the world leader we are the steward in the Department of Energy for world leading high performance computing. We just delivered the first exascale machine at Argonne. We expect Aurora, the second one, to come online soon. And then at Livermore, El Capitan, which will be later, that's stewarded by the Office of the National Nuclear Security Administration. Our basic energy sciences portfolio is our largest program in the Office of Science, funds all sorts of material science and chemistry, fusion energy science, biological and environmental. These are sort of self-explanatory, but just to give you a sense of the range, we are across the board the largest single funder in physical sciences in the United States. So what I was going to do next is kind of give you a couple of examples of recent initiatives that we've launched, particularly focused on climate, and then talk a little bit about some of our new programs that are focused on expanding and broadening participation in the Office of Science programs. And then happy to take whatever questions you have. So I'm going to get pretty narrow here on the Office of Science, but I'll do my best if there are questions outside the basic science side. So one thing we've launched recently at the Argonne National Lab is leading for us is something called the National Virtual Climate Lab. So in the course of the COVID pandemic, we launched something called the National Virtual Biotechnology Lab, which turned out to be an incredible mechanism in a basically fully remote space to coordinate the activities across our national laboratories to advance solutions to what we were facing in COVID. So the vaccines that reached the market, a lot of those depended on characterizations at the light sources at our user facilities. The countermeasures that were developed depended on things like the advanced photon source at Argonne National Laboratory. These user facilities were used by the industry, by researchers to characterize proteins, characterize potential molecules, and then deliver solutions through clinical trials. And they were also using our high performance computers to model those things and understand what the impact would be. So having learned that lesson, we're looking for other ways that we can coordinate across our national laboratories to provide sort of a one-stop shop, a front door for particular areas. And so the National Virtual Climate Laboratory was proposed as the Biden administration was coming in, and is a way of providing a one-stop shop for the most up-to-date information on climate science that we have across our national laboratories, and to make sure that we are speaking to communities on the questions that they have and the research challenges that they need answers to. The goal here is to provide better access for local and regional stakeholders, and as well as connections to HBCUs and MSIs. This is two of the key priorities for this new program, and you can now find that on the web. Another one I would highlight is something called the Urban Integrated Field Labs. So this is an effort to invest in the urban impacts and understanding the urban impacts of climate science. We've launched 4 of these so far in Baltimore, Chicago, the Gulf states, and Arizona. This was based on a competitive solicitation. We expect to invest in more of these in the future and build a network of these facilities, these field laboratories across the country. These labs are led by minority serving institutions, but have contributions from other entities, national labs, other institutions. And they bring together not just those research entities, but also community partners and local leaders to try to understand, again, what are the questions that we need to answer in order to help people address the impacts of climate change. And sometimes that is as simple as asking the right questions. The questions that we are interested in as scientists may or may not be the ones that folks in the community are interested in. And so this is an effort to bring the science to people and coordinate those discussions so that we do a better job of that. And so in addition to all of that, as I mentioned earlier, one of the key pillars for the Office of Science is really the people, right? We need to build this workforce of the future that understands how the climate is changing and what we need to do about it. And so those are all big thrusts of these investments. I mentioned the Earthshots. Another thing that we've recently launched is the Energy Earthshot Research Centers, as well as the Science Foundations for Energy Earthshots funding opportunity announcement. These are out. These are now closed. The pre-proposal stages are now closed, and we'll be making announcements on these soon. But this is a modality of investment you should expect to see from the Department of Energy's Office of Science going forward, trying to really get at the scientific underpinnings, the basic research challenges that stand in the way of reaching these Earthshot goals. So we, earlier this year, announced $200 million for the Energy Earthshot Research Centers over 4 years, and then $150 million for the Science Foundation Awards. In addition to these climate initiatives, I would say another big pillar of my boss, Dr. Berhe's priorities is really, like I said, broadening participation, making sure that she always will, if she were here, she would tell you, it's always been the case for me as a publicly funded scientist that I know my work has to serve the public. I have to be able to explain to any taxpayer on the street why their money should go into my pocket to do the research that we do. And so part of that is making sure that the work that we do actually supports the whole public and doesn't just support a small group of folks who have always been part of that community. So we're doing everything we can to reach out to communities, engage with them, make sure they understand the opportunities that we have, and make sure they feel included in the process. So I would just point to a couple. This is part of what's called the Justice 40 initiative that the Biden-Harris administration launched at the beginning of the administration. A lot of this is focused around addressing this initiative is focused on confronting and addressing decades of underinvestment in disadvantaged communities and the disproportionate impact that certain investments like in energy infrastructure have had on those communities. Now, a big part of that has to do with pollution and environmental hazards, which are outside the bounds of what the Department of Energy's mission is. But there is a huge part of this that's focused on climate change. And so making sure not just that the solutions we develop take account of justice considerations, but also that they're being developed with those communities in the room at the table. And so that's why it's so important that we're investing in programs that bring people into the fold and broaden participation in the Department of Energy programs. So 3 that I would highlight for you in the Office of Science in particular that we've launched. So Renew is reaching a new energy sciences workforce. This program is focused on workforce development projects that bring together national laboratories and minority serving institutions and HBCUs to develop the next generation energy sciences workforce, to make sure that those folks see a pathway to energy science, the energy sciences workforce. Funding for accelerated and inclusive research is focused on investing in the infrastructure at institutions that have historically not been part of our community. And so whether that's scientific tools or laboratories, those kinds of things, this is another program that we have. And then the third piece of this cuts across everything that we do now, which is called the peer plans, or promoting inclusive and equitable research. Most of you who have applied for research in the past are familiar with broader impacts from the National Science Foundation, other similar types of things from other agencies. This is the Department of Energy Office of Science effort along those lines to require every proposal that we get to provide us with a plan for how they're going to promote inclusive and equitable research. So many of the laboratories have stood up parts of offices that are helping researchers plan for those peer plans to make sure that that effort is coordinated across the laboratory. And I think many of you are familiar with these types of plans from other agencies. And so this is an important cross-cutting effort that we've instituted at the Office of Science that is new under the director, the current director. And then for the students and faculty in the room, I just thought I'd mention a couple of our workforce development and faculty programs that are really wonderful. And I think the thing that makes, I'll just say, I think the National Science Foundation is where a lot of this work in STEM education and workforce happens. But the unique thing that the Office of Science and the Department of Energy bring to this is the connection to our national laboratories. We steward these incredible facilities across the country. And so we bring experiences that link to those national laboratories in a unique way. So the science undergraduate laboratory internships prepare students for STEM careers, connecting them with mentors at the national laboratories to do hands-on research, discovery, learning, and professional development. This is open to undergrads and recent graduates, and we have 3 terms throughout the year. For faculty, we have a visiting faculty program, as well as many labs have joint appointments programs that are run by those laboratories. This is for enhancing research competitiveness and strengthening the STEM teaching at our universities. The visiting faculty have research collaboration opportunities with national laboratory researchers, access to facilities and resources beyond just being able to apply to the open calls for our user facilities. And faculty members from all institutions are welcome. I think that's a misprint there. All institutions. Fall, spring, and summer terms again for the visiting faculty program. And then the last one I'll mention is the Office of Science Graduate Student Research Program. So this program, graduate students come to do part of their PhD research at a US national laboratory, anywhere from 3 to 12 months in collaboration with national lab scientists. We have one new thing that we have instituted for all fellowships across the Office of Science is to make sure that we're paying folks a living wage. So for all of our fellowships, the stipend is at $45,000 a year now, up from I think around 30 or 35. And we are asking in our other funded programs that universities also consider paying their students at that level. There's 2 application windows, and this one is currently actually open through May 3rd for the current cohort of fellows. So I encourage students that are interested in this, connect with faculty here, including folks here who have connections to the national laboratories to identify potential mentors and opportunities that might align with your research interests. That went a lot faster than I thought it would, probably because I was talking too fast. And that's actually the end of my talk. These are some resources that I thought I'd put up for you, some links and things, which I think can be shared after the fact. And with that, I'll just say thanks and welcome your questions.
Thank you, George, and
Yeah.
we have time for some questions. Yes.
I was wondering if, when you're talking about the National Virtual Climate Laboratory.
Yeah.
If you limit yourself to the United States, or is this an opportunity where you might be doing things internationally with other countries?
So I think this is just getting off the ground, but I envision that there'll be lots of connections internationally as well. All these folks in our laboratories who are doing climate science are doing so on an international basis. We have tons of folks across the lab that contribute to the IPCC reports and all of those things. Is there something in particular you were wondering?
I think it's very exciting, and I'm working right now with Morocco,
and
they speak French.
Yeah.
And I'm actually a French professor who does even more the business side of things rather than the science side. But you want to marry business science to make things happen.
Yeah.
You want them to happen internationally. If during the time when students are, in fact, learning to work together as they will when they get out of school, having a chance to work virtually with partners internationally sounds like an ideal setting. And there are a number of programs outside of the sciences that are encouraging that now. But I think the sciences, if you want to be truly inclusive, doing something that's more than English only might be also an opportunity for a program that's virtual that really doesn't cost you any more to get people there. So just thinking is in terms of that. I don't know that you thought about it or not.
No,
but it certainly would relate, and I think it would make a lot of sense to the United States.
Yeah, so that's a great point. There are a couple of different initiatives that I'm aware of across the national laboratories and the sort of government as a whole to make sure that we have resources available in other languages. Particularly, I think particular focus these days lately has been on Spanish, but I take the point. Yeah. Yeah.
So Earth shots.
Yeah.
Way that those are being funded now, Office of Science will be funding, for example, the EERCs. And then the applied offices and EERE and the Office of Infrastructure fund things, say in hydrogen. So you fund an EERC in hydrogen.
Yep.
They fund hydrogen activities. Where does the coordination between those happen? So those discoveries that might come out of an EERC should be transferred over.
Yeah. So I think a lot of that coordination ends up happening distributed at the laboratories where folks are working side by side on similar projects. Internal to the department, we have a variety of coordination mechanisms that we're trying to make sure that what we're doing in the Office of Science is informing the way that funding opportunities are developed on the applied and the deployment side. So we have some things called the joint science teams, science and engineering technology teams. These are sort of cross-departmental coordination teams that are talking about, here's the FOA the funding opportunity we're developing. Here's what we're going to be investing in. Is that relevant to the technology challenge you see? If not, how can we tailor those things so that they're more married up? I think there is the point that you're raising, Seth, is really the handoff question of like, how do those things move along the pipeline? And I think that'll just be a continued challenge. I think I've always been influenced by Norm Augustine, who said the best way to do tech transfer is to move people. And I think that that's true. I think we see a lot of that happen at the national laboratories where people doing some basic science see applications and then move into applied spaces or take entrepreneurial leave or go through the I-Corps program, for instance. And they're the ones who sort of personally are moving things along the line, but they need help from folks who think more in an applied sense. So I think there'll be a lot of work to do on that over the next few years. But right now, I'd say the biggest challenge this is my first time in government, and I'd say the biggest challenge is how to do coordination without just making extra bureaucracy. It's a very real challenge that I never really gave much thought to before becoming part of the Department of Energy. Everybody has a limited set of hours in a day, and you can only do so many meetings. And so asking a bunch of people to sit on a bunch of extra teams can be a challenge. And so we've hired somebody in the in the Office of Science whose sort of sole focus is going to be on, sure, her portfolio keeps broadening, but her primary focus has been on coordination with those other offices, making sure that the right folks on our teams are plugged in with the right folks on their teams to understand. So, this is the capability we have, or this is the science we're trying to advance, and make sure that that's informed by what's going on. But I think over the next 5 to 10 years, as these big deployment programs roll out, it's been a constant message from myself and my boss to others in the department to say, you need the Office of Science and its national laboratories, its user facilities, the research we do, because as you deploy things at scale, you're going to run into new challenges that you didn't expect to run into. So, we're talking about inertial fusion energy, right? All of those steps that you laid out earlier today are going to probably run into some technical challenges, some of which may require real science and scientific investigations to advance. And so if that loop doesn't get closed somehow, you kind of can get locked in there. But at the Department of Energy, I think we have the ability to close that loop in a really meaningful way. But it's gonna be challenging to figure out the right mechanisms to do that. I would not say there's a silver bullet answer inside the department right now.
Are there other questions?
So these short programs were done this year. Are you expecting to repeat them next year?
So these are all the Earth shots are all decadal goals. So they're meant to sort of align programs for a decade. Yeah. You may see new ones roll out in other areas. They're sort of building them around key areas where we need to reach the decarbonization goals.
Part of the competition, that should someone who missed out on the
Yes. Yes.
Are we expecting a next round next year?
Yeah. So in the Office of Science, it's sort of a good rule of thumb that about a third of our grants come back open for new applications every year. So I would expect within the next 3 years, there'll be another call for proposals. And as with any government agency, I can say only so much because we depend on Congress to appropriate our funds. But pending appropriations with additional funding, we would want to launch more energy Earthshot research centers and the Science Foundation Awards as well. But I think, one thing that when I talked about the different modalities we have these hubs and centers and things, and those are not necessarily static entities. They evolve over time. So they may have different partners at different times based on the capabilities that they need. And there are often ways to plug into those collaborations through, connecting with folks at the labs, going on their websites, people learning about the capabilities you have, and then identifying opportunities to partner. Yeah.
These initiatives will be independent of who comes in 2024.
So I'm a political appointee, as is my boss. These are important initiatives. I hope that they continue. We are doing everything we can to launch things that are sustainable and that are important no matter which direction you come at this problem from. But I can't speak for a next administration. They'll have their priorities. Yeah.
Well, thank you very much for this very